Okay, we are back on Grayscale School, so the 8, if I'm correct. So we'll do some magic with Fortran today. So GPU computing with a lot of different methods. So OpenACC, the HPC SDK with NV Fortran, of course, and some other surprise. So we'll not spoil you anymore. Vincent, it's up to you.
Thanks. So sorry for my voice today. I will be at the minimum level of service, but I'm pleased to introduce you to the joy on computing on GPU with OpenACC, OpenMP Target, and NV Fortran. Fortran is traditionally not associated to a lot of so-called software engineering, and we will see how a minimum amount of it with the facilities of modern Fortran will allow us to have a better code. Okay, so GPU are mostly about getting threads, lots of threads. And we need to clearly find this thread in our problem. We have to express massive parallelism, as was the name in the early 90s. It was all the rage to study massive parallelism. So getting directly into the fray, for GPU in Fortran, what solution do we have? The first one, the best distributed one, is OpenCL. It's everywhere, even out of NVIDIA, but it is very heavy. On top of which, it relies on binding to C, which is possible since Fortran 03. And maybe we would attempt some more modern approach with Vulkan, which is also everywhere, even out of NVIDIA, but is very heavy from an administrative point of view. You have to ask for a device, for a lot of things, because before you get in the real computation. We'll not look into any kind of details about these two approaches today. Know that it can be useful if you have so-called embedded processing in some very small and cheap ARM kind of boards. I speak about Odroid, I speak about Raspberry. They have their own small GPU that will not be supported by all the solutions we see today, but you may want to free your CPU for networking, for high-level things, while getting cycles and while getting computing power for your dedicated embedded program. Okay. So, as we are sacrificing to the god of GPU, the idea would be to bend directly into CUDA Fortran. The good point is to use as soon as possible all its libraries. I speak about QBLAS, QFFT, QRound. So, as we will see, GPU are not known for the interfacing speed. You take a lot of time and energy to just get the data into your GPU memory. So for a lot of simulation, if you can generate your random number, if you have some kind of Monte Carlo simulation, you will benefit of generating this random number directly into the GPU. Okay, so we have it we will not address CUDA Fortran, which would be interesting in the sense that it is believed to deliver the most out of your GPU. But we will directly address the three last possibilities: OpenACC, OpenMP, and NV Fortran standard parallelism. Why these three are interesting? Because we want to be able to start our development on simple CPU Fortran. We want to have code that we can test outside of all the intricacies of using a GPU. Using a GPU is some kind of martial art. You have to praise a good God that the good driver is installed with a good version. If we could keep it simple on the side of the developer, be the better. Okay, so what are these three variants? OpenACC is a set of directives, much in the same way we have seen OpenMP last week. These accelerator directives require you to explicitly handle the memory and tell the compiler what part should stay on the device, what part should stay on the host, what part will be copied from the host to the device, and what part will be copied back from the device to the host. Okay, device, host is your CPU, and device is your GPU. So 10 years ago, the world was well cut between OpenACC for accelerating cards and OpenMP for multi-thread. So OpenMP started from 4.5, started introducing a target directive. On target were in fact accelerator boards. So the model is the offloading model from OpenACC to OpenMP is slightly different, but we'll see it in more detail. So, of course, these solutions are nice. You set a flag on OpenACC, starts doing its magic, provided you have defined the correct data transfer. You set a flag on the OpenMP does its magic with the same condition, but if we would have nothing to do, it would even be better. And this is what NV Fortran tells us. So we'll see how much this is working and what caveat we have to address with this apparently so easy model. Okay. So up to now, we have seen different scale of parallelism. We have seen processes in well-separated environments. We have already discussed the so-called embarrassingly parallel problems. This is not a topic for this year's school, but the king of this processes level parallelism is MPI, with some concurrency coming from some competition coming from CUDA Fortran. Starting one and still limited one. As for thread, that we call lightweight processes, this is what we have been doing all the time last week. The easiest way for us is to use the shared memory on SMP. Also also, as we have seen, we have, as Joël reminded you, vectorization, which is closer to some kind of instruction level parallelism, which is some data parallelism. You have the same instruction getting to multiple data. So as we have seen in vectorization, the first part of the problem is setting your data in a way that will allow your system, your instructions, to properly treat, to properly manage this data. As Joël insisted on, for data contiguity, which is required for parallelism, we prefer a structure of array to the classical object-oriented collection of objects. Okay, so last week has clearly shown us that we need a three-pronged movement: parallelizing from the top, vectorizing from the bottom, and keeping the cache hot. In Fortran, we don't have the same level of metaprogramming that allows the magic of Eve to operate. So in order to vectorize things, and I insist on vectorization because as GPU programming is a really data-intensive kind of programming, we need to remind us these aspects of vectorization. So we may, as well as in C, but with the supplementary issue of getting the binding to the C libraries of low-level instruction, of so-called intrinsic instruction. Frankly, except for very specific cases, nobody is advising you this approach. The best way on what you can particularly suggest to your scientist colleagues is to use vector libraries as much as possible. And the ideal part would be to let the compiler do it, provided that we can, on one hand, express the data parallelism, which is a high-level aspect, and which is particularly sensible, in principle, with the way of Fortran 90 to harness the power of arrays, expressing, getting array expression, getting elemental function. If it's too complicated, expressing concurrency with do concurrent. On the other hand, we also know to hint the data contiguity and alignment to the compiler, which is a low-level aspect. We will address this tomorrow evening with some example in both C and Fortran to see clearly what are the differences between both. Clearly, at this point, Fortran is not in any good position to hint the data contiguity somehow with the contiguous attribute, but hint any kind of alignment with Fortran is up to now something that is not specified in any standard. So once we have compile our code, how to be sure that it was properly vectorized. We have compiler flags to report vectorization. So you have to know your compiler, you have to know your compiler's version, because the flag gets different depending on the version. They deliver you different kind of information. You can check the resulting assembly. You can do some part of this checking easily, but the learning curve is not quite easy. With the proper amount of Xanax, you can also use Macao. We'll see how it plays a bit now, more tomorrow. And indirectly, you can use perf to check that your kernel is executing with the proper rate. Okay, so another point, because Fortran, from start, was a formula translator. The goal, the soul of Fortran is you put some mathematics in it, it spits out code, fast code, good code. Okay, this is the contract. And sometime you will see old Fortran that benefited from complex numbers since the dawn of Fortran, but where people didn't know this, and they were implementing complex multiplication explicitly, for instance. If you look in the matlib or the libstd of C++ for the complex number, you will find a comment. I have not been checking in some years, but I'm sure it is still here. In this comment, they say this is high school implementation of complex numbers. So there is usually a lot to be won by a proper complex library. Okay, but usually using a complex number, it's a kind of symbolic vectorization because you have two data at once in one object. It's even more true if you use quaternion, which are the right way trademark to proceed with rotation in space. Nevertheless, this symbolic vectorization gets in the way of practical vectorization. As you see here, the product of two complex numbers does not allow any kind of regularity in the product on the sum of them afterward. So instead of vectorizing one complex product, you can vectorize 4 complex products if you have 4 lanes in your system, or 8, 16 if you want. If instead of storing your complex as a vector, one by one, real, imaginary, you put everything contiguous in all the real part of the A's and then all the real part of the B's. So if is a system that masterfully does it in C++, we have, to my knowledge, no such thing in modern Fortran. Okay, so this part about vectorizable code for cube-root will be seen in more detail tomorrow on the way to exploit it. as well as Macao on the way to tame his burst of mocking us. Okay, so let us now address GPU, starting with the slides of Pierre. In a GPU architecture, you have a large set of streaming multiprocessors that benefit from the memory and share a common L2 cache. In your streaming multiprocessor, you have lines of core that simultaneously fetch, decode one instruction for multiple data. You have some common execution context on shared memory. When you add up multiple such parts, particularly when you extend them with tensor core, you have the modern architecture of GPU. So thanks to Adrien Gralond for this link to an array of, which is the Rosetta Stone of what is a SIMD lane, how you would express on the CPU side some term, how it translates in NVIDIA terminology, and how it expresses into Chronos terminology. This makes the reading of any kind of literature about GPU an exercise in translation. Okay, so before addressing the programming of GPU, you will have to get friendly to your operation team because a GPU setup is something that is almost unique. You have your operating system, you need some driver to discuss with the kind of GPU you have. Depending on your system and on your GPU, you have a range of possible value for the driver. So you need to be able to check that you have the right kernel with the right CUDA version and the so-called right compute capability. So sometimes your compiler on all the GPU will tell you, oh, this, I can't do it on this compute capability. So we will be aiming today at reaching for the most generic and compiler version and so on independent way of expressing a GPU parallelism in Fortran, but it's a lost war from the start. So we know that our code will depend on the kind of GPU we have. So as you can guess, here it was the value of the NVIDIA SMI report last year on the same compiler. Let me check it now. Okay, so we now have 20 points on the version of the NVIDIA SMI driver, NVIDIA SMI program, NVIDIA SMI driver. The CUDA version was 12.6, it's 13. this is the same RTX A4000 laptop GPU. It is taking 1/6 of energy doing nothing. So you better have a good reason to use it. And that's it. Okay, so just to frighten you, some people tried porting a GPU with Vulkan in Fortran. It leads to this kind of administrative form where you redefine the constants, you simulate Vulkan types with C binding. So this is possible. People did it. And here, you create an instance, you destroy an instance, you initialize the graphic windows, you create the window, you terminate the window, you destroy the window, terminate and destroy. Okay. So we would like things to be easier than that. If you want to try some CUDA Fortran, you will use NV Fortran with the option CUDA. Your program should end with CUF for CUDA Fortran, with capital CUF being CUDA Fortran with some preprocessing before. And okay, this is not a Hadamard product, but this should not be very different. That you can express is, here is a bit surprising compared to what we do in standard Fortran. We don't express the loop. We don't express the loop. The index comes directly from object that CUDA Fortran deals for us. We have block IDs, we have thread IDs, and this is what generates the loop index. So CUDA Fortran is certainly very powerful, but it will not in turn, it will in turn require you to rewrite many things. So why is that? So you can keep the nice keywords such as pure, but you have some extensions, you have attributes global that qualify your so-called kernel to run on both the CPU and the GPU. If you want then to test your SYCL kernel in CUDA Fortran, you declare your CUDA Fortran program as usual, as a normal Fortran program. You use what you defined in last slide in the module matops. You use matops only function SYCL, and you use some CUDA Fortran module that defines Team3 operation for you. And you have your grid, which is of type dimension 3 on T block. And then, starting from a T block, you construct, you build a grid according to the size of your problem. Here I put it in a parameter, but I'm sure you can proceed in the same way with dynamic variable. Okay, then something is quite powerful. So you have this extra attribute that did not exist in simple Fortran, but which exists in CUDA Fortran, which is the device attribute. It means that beside your two sets of dynamical array, of statical array, X and Y, you have X on device, which is a device variable, on YD, which is also an array on your device. So the way to transfer the data is easy. X on the device equal X on the host, and the same for YD. So you have the array expression familiar from standard Fortran, and then you have this call of a kernel with three symbol, three lesser than and bigger than brackets. So you pass the parameter to your procedure, and you have the return, sorry. You pass value because this is standard Fortran that allows you to pass a variable like in C, which is not the standard default by Fortran, as we will use it today. And you get the return of your computation in the Y vector, which is also an in vector because you modify it in place. Okay, so you set the initial values, you call the kernel, but as you apply it on the device, being defined globally, it is executed on the device. Okay. So CUDA Fortran clearly requires some rewriting. And one of the classical examples I use is the first computation I had to accelerate. It was the computation of electron capture cross-section in the core of a supernova. So you have all had the story of, in a supernova, the pressure gets so big that the degeneracy pressure of electrons in the matter can not be enough to protect them. So the most stable configuration is for the electron to get into the proton and produce a neutron plus a neutrino. In your view, how many free protons do you get in the core of all the dying star? Not many. You have a lot of iron atom, some neon, some carbon, some oxygen, some sulfur, but not many free protons of hydrogen. You have some, but not many. So the colleague of theoretical astrophysics, theoretical nuclear astrophysics, wanted to take into account the nucleus aspect, nuclear aspect of this capture of the electron. And they wrote a very strange mixture of C, because they didn't know how to have dynamic allocation in Fortran. So the surrounding of their program was all Jurassic Fortran, and the inside part was in C. Besides a factor 50 of optimization that could be obtained before parallelizing anything, it was a mess. So after this initial improvement, I wanted to exploit some parallelism, because the whole program was this very big nest of loops with 5 levels of nesting. The very nice part of 5 level of nesting in this way is that you have between billions and hundreds of billions of computation to be done. You have massive parallelism to express. Unfortunately, OpenMP with this kind of old Fortran with a lot of commands which are global variable was a difficult beast to tame. And I got a segmentation fault in the midst of Intel C++ and Intel Fortran interaction. So colleagues in Idris suggested me to convert everything in a single language, which of course I chose to be Fortran 90. The validation of the result occurred rather fast. The speed was still the same. But now I had 3 ways to produce the segmentation fault instead of 1 because G Fortran, NV Fortran, at the time was PG Fortran, and Intel Fortran would lead to the same result. So classical idea would have been to use Valgrind, but this being a mix of old Fortran and modern one, I had still a lot of statically declared large array, which made Valgrind tell me, no way. No way to address such a large static space for Valgrind. Okay, so in order to get further, and as there was a clear amount of parallelism to be used, I rewrote everything yet another time in order to best express the parallelism. And for instance, one of the routine, so you see I kept this 5 level of loops with some mask avoiding some kind of computation. And all of this is a standard Fortran except for the accelerator directives. So I must declare at the interface what is the data contract between the host and the device. I tell the compiler that if you already have some mask kinematics array defined in the GPU, you don't do anything, else you create it. So this is declaring the variable that will be discussing between CPU and device. And as you see, this radproint1 array that I just allocated will be filled as a sum of product. But come on, Vincent, is it not a matrix product? Why a sum of product? Why not use .prod, which is the simplest way to express this line? Why not? Why didn't I use matmul, which would have got me rid of, in fact, all this nest of loops? And the problem is the one I just suggested before. It depends on your compute capability. It depends on your CUDA version. This was almost 10 years ago. And at that time, CUDA Fortran, PG Fortran, told me, oh no, this, I don't do it. So, I told you before, starting from the initial version, I had a factor of 50 without parallelizing anything. Then rewriting it in this way, without accelerator, without GPU, the simplest CPU version of this new rewriting already got me a factor 2 on top of the 50. So we are at a factor 100. And provided I had enough memory on the given GPU, I could benefit from this ACC for, in that case, a factor 7. So on total, it was a speedup of 700 from the start. At the point I did this, it was the evaluation of this array that had no expression of parallelism that took most of the time. So to benefit of further progress, I would have to redesign this part, which has not yet been addressed. Okay, so now we have seen our dear Gray Scott kernel and what would it give to open ACC it. So we have the subroutine evolve that will compute as here one step. It will compute the Laplacian as the sum of the stencil times all the surrounding data in the previous version of U, and it will increase U0 according to the formula. Okay. So here in the kernel, you see these two kinds of, these two loops, this nest of two loops. So of course, being a Fortran column-wise order, your line index is the one getting faster. You have to order it by hand, but why don't we use do concurrent for this? And this is one of the problems of OpenACC, and it is the same problem for OpenMP. You cannot use do concurrent with ACC directive or with OpenMP directive. It's a pity. It's a pity, but I try to stay in the shoes of the compiler producer, and I guess that they would have to design some clever way of knowing, okay, I am in some OpenMP or ACC context, so I will not use the freedom that do concurrent allows me in principle, because I am in this specific context. So they chose not to take the risk. And so you get some expression that is a bit old-fashioned and that is not as expressive as you can expect from modern Fortran. Okay, so we want to apply the stencil kernel. And we just declare here that it is an accelerated parallel loop, and you collapse the two levels of the loops, because our two-dimension arrays are contiguous collection of data, in fact. The accelerated region between this $ACC data and end data exists even when you get into functions. The compiler follow your data, and you can only ask parallel loops when you are in some data region. So we specify that the initial value will be copied from the host, and the return value will be created on the host before being filled here. Okay, so OpenMP, on the other hand, is not very different. So maybe for some of you who already have some OpenMP CPU experience, you can keep your program as a whole with some parts, depending on the GPU with OpenMP offload, on some part being processed on multi-core. Very much in the same way, we have some target data region on end target data. Instead of copy and create, we have map to and map from. So it's really to say we have something different. And here we had the choice between two statements, and we decided on OpenMP target teams, loop, collapse, on bind teams. So the syntax is correct, but the lexicon is a bit specific. Nothing changes much between both of these. But what we really would like to see is this NV Fortran do concurrent. So we have still the same routine, subroutine evolve. On here, for each iteration, not parallel, we have the do concurrent directly encompassing the two levels of the nesting. Okay, I kept this garbage of old Fortran to compute the Laplacian, but why bother with it? The sum of the stencil times the neighbor is so much more efficient. And so you see that with this, I expressed my kernel and I leave it to NV Fortran to put it on the GPU. It's too good to be true. It's too good to be true, so we'll start showing our expectation. What will go wrong? Okay, so with this, we have the best way to express concurrency, which is do concurrent. It is both explicit, compact. You don't have to deal with the nesting. You provide the range of your variable and you leave it to the compiler to get it in the right order for you. So there is a lot at play behind the scene. So this is way, way better expressed than with these old do loops where there is no guarantee of concurrency. Why is this not the absolute good? Because when you express CPU Fortran, you will not only use do concurrent, you will use two other aspects. You will use array expression and elemental functions. You will use as well some aggregating function. You will use sums, you will use products, you will use dot products, you will use matmul. On NV Fortran, doesn't take it by itself. If you want NV Fortran to convert your parallelism in the easiest way, as this way is expressed, you need to provide NV Fortran with do concurrent expression. So some of the part of your code that are already expressed in a very nice and synthetic way with array expression, matmul and dot product, you will have to rewrite them by hand with do concurrent if you want NV Fortran to do the job for you. It's surprising at first. Okay, so we have not yet reached the best possible case. So, to summarize the GPU in Fortran practical problem with NV Fortran, you also have some issues. NV Fortran is a very aggressive compiler. This is a good thing. We'll see tomorrow that for vectorizing is really good. But they are not very respectful of the subtleties of the norm of Fortran. We will see some example today with our dear Grayscott code. To say it's surprising is 10 years ago it was surprising, but now some kind of habit is setting in, and it's not a satisfactory habit. Okay, so once you have used NV Fortran, and even with the right amount of parallelism expression, sometimes you have so much parallelism that it exceeds the memory of your GPU. So you have to redesign your problem. So it's easy, but at some point you will have to adapt. So up to now, one of the solutions of this problem is to have multiple GPU. And the easiest way to address this problem is to get your program separated in multiple processes, each of the processes addressing one separate GPU. So you can do this in OpenACC plus MPY. So with MPY, you set different processes out of your program, and each of them is in charge of a separate GPU, and this GPU is addressing a limited part of your problem. Okay, so this is some way to express very large parallelism. Okay, so all of this goes against the Fortran purpose, which is to express the math and leave it to the compiler to translate. But at some point, we have to be reasonable, and for a lot of problems, NV Fortran benefits are really, really big. So maybe we need some kind of prepilation, domain-specific language to cut our problem to NV Fortran and then to compile it for a given GPU. So as a conclusion of this introduction to GPU in Fortran, I would say that NV Fortran is a very nice way to turn your years of experience in Fortran to GPU programming. You have an easy access to performance, and you have a clarity of intent in your code. But, as I have said, we have a lot of caveats. we have a lot of points to address, and we will not benefit. It will not automatically turn into something which is fast and efficient. There will be some bookkeeping. Okay, so before we address the code of Grayscott, is there any question? Maybe I should look at the Discord. So thank you, Pierre, to started answering. Okay. So I will address the question of Shifang Li. Why only vector after if? What if put vector in the outer layer of loop? Okay, so this is a good question because I did not enter in enough tricky detail, but it is a bit disappointing to have to enter to this detail. So, as has been repeatedly explained about the architecture of GPU, you have level in this architecture. You have things at the level of the multiprocessor, and you have things at the level of the whole GPU. So the first three loops that are collapsed together are dealt at the highest possible level, but we will benefit of the SIMD treatment that exists inside the streaming multiprocessor with this vector independent thing. So you need, in expressing your massive parallelism, to be able to fill as much as possible your SCMD lanes into your streaming multiprocessor. The GPU will manage somehow to have some streaming multiprocessor do nothing out of some lanes. So you are losing performance if, in some case, you can redesign your loops to do things better. In some case, you cannot. So depending on the size of these two loops, the product of n sims plus 1, in this case 32, times the number of configuration, which is anywhere between 100 and 500, the product will not specifically be a multiple of, okay, in this case, we have something close to 32 in the top loop. So we will fall short or over by a small factor and will not lose a lot. But it could not have been the case if the number of Simpson iteration, because this is thought as some integration. So if the number of Simpson iteration are not had the good luck to fall right on this 32 factor, we would not have benefited from the best optimization from GPU. Do you feel the explanations enough? Okay. Yes?
Yes. Ça marche. I had a question about slides 24, 25. Yesterday we saw JAX in Python that which had us reformulate for loops into some sort of functional style programming. Is this what we're doing here?
In some sense, yes, because the CUDA kernels are telling you that each data is on its own lane, which is a thread of the GPU. So the thread is the logical equivalent to the core, the GPU core, which is the physical side. So you need to be able to match one thread on one core. By getting this kind of indexing, this I here, you can match both in view of the compiler.
Thank you.
About the disadvantages of do concurrent. Okay, so yes, if you are writing new code, on this is a toy model, on you don't expect the parallelism to get so massive, it is best to start using array expression, start using the standard given functions such as sum, dot product, product, which is a Hadamard product, matmul, write Fortran at the highest possible level. Use do concurrent instead of do loops. Okay. I remind you here, okay, so you see we have these three loops. If it were not with OpenACC, it could be a single do concurrent loop. And not only we would have transformed these three lines into one, but also this if mask kinematics on these two highest level indices were true or false, we would have integrated this mask into the do concurrent statement. Do concurrent statement do not only congregate do loops, they also allow you to have masks. So here we have the possibility for a much more compact expression. But okay, with do concurrent, we lose the possibility to have OpenACC. Okay, but maybe this program would benefit from a rewrite to NV Fortran, STD parallelism. Besides this, we would have a second do concurrent loop inside. And maybe, I've not tried it, we could even, as we would not be in the ACC context, compress all these 5 levels of nesting on the mask into one do concurrent expression. So this transforms radically the way your code looks. But it is, in some sense, some one-way ticket. Because with this expression, you lose OpenMP, you lose OpenACC, you only can do it with NV Fortran. Or on the CPU side, with any modern Fortran compiler. Okay, so this was the first part of the answer. Do concurrent is really, really nice. But then here, as I told you, this sum of product, I could also express it as a dot product. And when you have a loop of dot products, it's in fact a matrix product. So the best way would be to express this large rat-prorint array as a matmul of this WF1 reshaped array on this Bessel function int array. But then NV Fortran will not tell me, oh, matmul, of course, I put it on CUDA BLAS. This is what I would like. I would like to replace these 12 lines of code plus 3 lines of directive into 1 line, maybe 2 to be clear, of matrix product. And that NV Fortran gives me, yes, this is a matrix product, you have a GPU, data on GPU, let's go. To my knowledge, this is not yet the case. So this is why we have a lot of way to express, a lot of satisfactory way to express parallelism. Matmul is very good. Do concurrent is rather good. But when we use one, we lose some possibilities. Okay. Okay, so for the second part of your question, Shipeng Li, about do concurrent plus OpenACC dealing with pure subroutine, reduced shared memory, in case no explicit memory management is needed on rewriting. Can be at minimum. There is some effort in rewriting your code. You need to have as refactorable code as possible, and that's why you need a lot of unit tests. So you see, like in a fugue, the theme of the school is coming back and back and back again. So if I want to run on an AMD-based machine, better not do concurrent. If you mean HIP GPU, I have no idea the level of support of their compiler. If you mean AMD CPU machine, yes, do concurrent a lot, but depending on the case, you can express it as a matmul, and maybe they deal better with it. Okay. So, let's look at some code. So let's start with what we had last week. The size is good enough? Okay, so last time we had put most of the computation in a module, Grayscode settings, where we have a lot of data structure describing the problem with some parameters on some of the variables that will get from input-output in a name list. The old Fortran way that is not well known enough for parsing data. We will store the data to some shared memory image file. So this is a dirty trick to avoid losing too much time on input-output. Besides, we have also the logical flag to not write by default, concentrating on the time we spend on computation. Every 32 loops will stop for storing to input-output, provided that to write is true. Here, I have settled on the old Fortran style of getting a logical file number, logical unit number for the output file on the input file. I let it slip, this input should be here. And I have default value for the time steps, the diffusivity of both species, and the feed rate. And I started to explain about the various possibilities of stencil, and we choose one, which is one of the keystone of the school. And then the nice idea we had last week was to use pointer instead of allocatable. And the purpose of this subtle change was to be able to swap the field by swapping the pointers. What could go wrong? Okay, so the update routine here is the one that will decide when to write one of the slices of the code. And on the CPU side, so before we would do 2 steps of evolution in one iteration. Here is the reason for this divided by 2. For each step, we compute the Laplacian, compute the new value of U1, compute the Laplacian of V, compute the new value of V1, and then we do it back. So this is ugly. On your left, the solution is really ugly. And on your right, thanks to this swap field function, this is much better. This is clearer. On the CPU, it's as fast. So, contrary to a very old version, okay, contrary to a very old version, we don't copy back V1 on V0 to address the next step, which would be a loss of time. Okay, so on the right, as we know, have pointers. We need to delete fields. Fields are pointers, so contrary to allocated arrays, they don't stop existing at the end of the unit in which they are defined. So this is explicit memory management, and you can get into problem if you don't do it properly. Certainly, in a more object-oriented approach, we would specify this delete field as a final procedure, which is the equivalent in Fortran of a destructor. You have no explicit constructor statement, but you have a way to implicitly construct your new data structure in Fortran, but you have final as a keyword of the language to tell that this routine should be addressed at the end. It can be an interesting exercise to do it here, but even if I have some module, I have not defined a corresponding type. Class-oriented programming is marrying a module and an abstract data type. Here we have old-style modular programming. Okay. So let me move to the solutions. Come on. Okay, so depending on the version of the image you have, you will need to source something that is in the example GPU. Okay, let me get it bigger. Okay. So you can find in in the GitLab this example GPU NVIDIA SH, which is a bash script with all the environment variable you need for your HPC SDK, and specifically the NV Fortran aspects. So in order that this variable stays with you after execution, you will source this file and not execute it directly. And now we can ask NV Fortran what version is at hand. Okay, 25. Oh, yes. So if you are working on the image, you should get at this level 26.3. The 26.5 appeared just during the start of this call. But as you will see, there is a lot to be addressed, a lot of correction to be addressed, even in this modern version. Okay, so we'll start simple. We'll start by compiling this very elementary pre-OpenMP version. It's old Fortran, not Jurassic Fortran. It's old modern Fortran. Let's say pre-classical Fortran. And we find every aspect of it here. So we want to compile it. We'll always ask for debugging. We ask a lot of optimization. As you can notice, if you look, into, for instance, this version that we compiled last week. Okay, for the size. I've done something very bad. I've not put any implicit none. So why do I allow myself such a lax approach to modern Fortran? Because I know that I declare everything, so it would just hinder my code, and I have some mdecl check. This is the declaration check of, declaration check of NV Fortran, which is the equivalent of asking for implicit none. And when you compile with gfortran, the most popular Fortran compiler, you can use -f implicit none to automatically consider that everything has to be declared. Okay. So with this, everything should be good. So I need to rely on some wrapper around the HDF5 library. Then I need to use this floating point precision module. Okay, so I did not put it here. It is back in the source. Okay. Then I need these grayscale settings. And up to now, everything is in it. And last part is the main program. Okay. Then we'll compile it as the executable grayscale pre-OpenMP. I missed a lot of things. From this part, the HDF5 utils will require some link to where do I have the modules of the HDF5 library. So this is the time for point about the good and bad parts of modern Fortran. So in Fortran, contrarily to C, C++, you don't have header file. Yay! So you avoid duplicating things. But you can do it because the header file is generated from the module. Okay, why not? So what will be the equivalent of the header file is the mod file. But the standard, in his wisdom, has decided that it was up to the compiler implementer. So G-Fortran has some standard for the module file, and V-Fortran has some standard for the module file. Intel Fortran has some standard, AMD Fortran has some standard. They are all different. Some are binary, some are text. It's a mess. When you rely on some external Fortran library, you have to recompile it if you want to include it with the code you want to use. Maybe in the future, if enough people write to the ISO committee, please write to the ISO Fortran committee. We will rely on you pushing for things that we want to appear in modern Fortran. Maybe something like what is happening in MPI 5 will also happen for module file. In MPI 5 version, they have decided that there is an interoperable application binary interface. So we would need that the mod file get some standard between compiler to be interoperable. Oh yes, by the way, I forgot this one. When you move from two versions of your compiler, from one version of your compiler to another, there is no guarantee that the former mods are still good. It was particularly the case moving from G-Fortran 14 to G-Fortran 15. So good luck. Okay, so I think we are about to take a 30-minute break and have a good coffee for we'll be Fortraning much more. Welcome back to the second part of the Fortran GPU Day of the Grayscott School 2026. So we were dealing with the way to express, to compile code relating to libraries where the equivalent of the include or header file are depending very much on the compiler, the version of the compiler. And if we look at the library at play here, we are interested in the HDF5 libraries. So as you can see, we have tons of them. We have some old version. Okay, so in the Docker image, you will have this HDF5 2.1.0 -install. Here I checked that it also compiled with the AMD G-Fortran on Intel compiler. The one without this kind of information is the NVIDIA one, as this is the topic of today. I also compiled the most recent one in case, but for the one using the Docker image, you will keep only this one. I have some former one in case I needed some kind of point to get back to. The one called purely /op/HDF5 is indeed pointing to the 2.1.0 NVIDIA one. So maybe on some Docker image you can benefit from this symbolic link, but it has not been tested thoroughly. So what I suggest is that we export some variable HDF path as this. In this way, we will be able to also include the this path /include. So let us just check it is meaningful in our case. Sorry. So as you can see in the include, we have the HDF5 C header, the .h, as well as the Fortran header. So out of curiosity, what does it look like? We will start wondering, okay, so good news, module format of the NVIDIA Fortran compiler is a text version, but as you can see, it's not quite explicit about its meaning. We have a list of module and libraries plus numbers that are clearly of no interest. Among the binary versions, if we look for other one, the new Fortran one are in fact gzipped compressed one, so even if binary, it's another version of text file, you find the same kind of garble, but all of this is incompatible. Okay, so our command was as follows. We want to include this, but this is not all, because in the end, we also want to link with the corresponding libraries. And so we need HDF path lib. And not only we have to specify where are the libraries, but we have to specify which libraries. So depending on your system, if you're on Debian, the name of the libraries are not the same. Okay, here we are on Debian, but using NV Fortran. If you are on the CPU side of things, and you want to use your local library without recompiling it, you have some serial HDF5. So the naming of the libraries is a bit different. Okay, should we compile? What will go wrong? Nice, we compiled. Okay, maybe we want a bit more information. So before it gets me suggested, before it gets suggested to me, I will share with you the command line here. But we want to do better because the compiler can tell us about the informations on the warning. Okay, so we'll add 3 more options before the declaration check. We want the compiler to report on its optimization on our code, minfo = Excel. We want the fast option, so I'm not quite sure if it's the same thing as fast, and if it allows bad things with modifying the mathematical expression, but we'll care for numerical things later. And we want all the possible warning as any modern developer. Okay, so no optimization displayed up to now. This is the pre-OpenMP version. Well, does it work? Before running, we want to check what impossible computation will be asking from this poor beast. Okay, up to now, we are still on the CPU. So 32,000 may be too big a step. Okay. VI is really for the hard days. So, as you can see, we have the standard parameter. On here, we say that we'll write HDF5. So we compiled this and we'll time it. Okay, so microsecond on parallel with do concurrent. That's okay. About 1 second on CPU for 320 image. It would mean 100 seconds on CPU. As we have not invested a lot in this aspect of the code, it's slow, but not stupidly slow. For the real problem, we would need 100 seconds. Okay, and as we want to produce a movie with 40 seconds of image, 1000, it means we are only a factor 2.5 of our objective. But we'll do better. Okay, so the next step from here is to so we had this code. On the evolution step in it was vanilla Fortran. Do loops all the way down. And the bad thing is that we copy the value to we copy the value back, so here we lose time in the second step. So we should be able to do better. Okay, so you can find in the solutions as well some OpenMP variant. So I'm showing you how to recompile what we had compiled with the CMake last time with Fortran on CPU. I show you how to recompile it on a CPU with NV Fortran. So if now we take Grace Code settings OpenMP F90, okay, we'll ask to accelerate with multiprocessing. This OpenMP F90. Okay, multicore, ACC égale multicore. So let me check once more. When I want to use FOpenMP, no. Okay, so depending on the version of your compiler, you will have different warning message. So it's a general good rule of thumb that when you try to address fine points, you should compile with as many compilers as possible. Okay, so for most of the aspects of today, only NV Fortran will do it. But even in the old time, compiling with G-Fortran FOpenACC was stricter on the standard aspect of things. So it would help you write better OpenACC directives. And here, we have a ton of warning plus a severe error. So this new version of the compiler, compared to the one of last year, doesn't want to take our new OpenMP code into account. Not so good. Okay, so maybe as the day is the day of GPU, we'll turn directly to the OpenACC version. So if we meld it, if we compare it to the Grace Code settings pre-OpenMP, okay, what do we see? So now we have put the loop in some compute subroutine, which is nice. We have, as said in the slides, introduced the data region and some ACC parallel loop collapse in the compute version, as well as for the really not efficient update, which is copying arrays. Okay, so when we want to compile this, so I don't copy this command line as it is no more working with a recent version of NV Fortran. We will use accelerator and introduce our first reference to a GPU in the code of today. Okay, beside this, so I'm also changing my source code, the OpenACC one, and the name of the executable. Okay, so we have more interesting things. We have been asking for information about acceleration. In the evolve part, which is this one, there is a copy region, and in evolve in line 104, all the statements that you have provided in your ACC directive are used. U1, an array is created if not already present. You copy U0 and V0 from the CPU to the GPU. So you always have to take this into account. And you create, in the same way as U1, some array on the GPU. So this is exactly what we have been asking. And then the next step is inside compute, and this is also what we are expecting. So it tells you that inside compute here, so the line is 121. In 121, it is generate implicit first private, so you it reminds you about some OpenMP terminology. Each thread will get its own value of nx and ny, which will be separate, but initialized with the one of the main thread, which is the CPU thread. And it generates GPU code. It gives you the details you were not asked to provide, but that will help you in a later step when you will want to look for more performance. It tells you that the size of the vector, the size of your same instruction, multiple data units, is 128, and it collapses the two loops on block IDX, thread IDX. So you have some hints about the CUDA that gets generated by OpenACC. So if you are moving from one technology to the other, using this kind of information will be of much use. So, okay, we'll not detail all the aspects of provided information. And in the end, there is a copy out of the data that have been computed. So update, you remember, is the part that is stupidly copying the code. Well, we have something. How well does it run? So let me copy it for you. For Joseph, mdecl check has a G-Fortran equivalent. So, okay. I first send this and reply to this. This is -f implicit known. Okay, so this is a nice time to speak a bit about implicit known, since Fortran 2018, implicit known got extended to two nuances, type and external. So the standard implicit known is type. There should be no implicit type defined. So this is what we all Fortranists know about implicit known. But F implicit known external means that you need always to provide a full prototype of all the functions you will be calling for in your compilation unit. So this is a much stricter requirement. And unfortunately, NV Fortran is not very familiar with this new Fortran. They selected, they handpicked the aspect of Fortran 2018 they wanted to see happen. But okay, they are fast, so we will be very forgiving to them. Sometimes. Okay. This one. So yes, if you can use F implicit known external in your code, I strongly recommend it. It's a very good practice. Okay, first GPU run of the day. Fast. Okay, maybe even faster because there is the time to warm up the GPU, exchange things. Let's move the cursor by factor 10. Okay, 1 second for 32,000, so we'll be at 10 seconds for the final goal. So we always display a little something in order not to be alone. Okay, 10 seconds. But 7 of real CPU time. Come on. It's not bad. The CPU version we had just before would have been 100 seconds. We have a speed up of 10. Yay! But our code is a mess. Seriously, we don't want to see these kind of things. Okay. So, I've promised you some OpenMP target. We should, so this is not the OpenMP, but the OpenMP offload. Okay, so this is the one I described in the slide. So sorry for the French, but here in the update part, which is definitely not the way to go, where we copy back the U1 on U0 and V1 on V0, I tried to express it in a modern Fortran way. So not expressing the loops, with some OMP parallel region, letting the compiler decide on the best way to express this. And last year, this aspect was not as interesting as the naive loops. So you see, sometimes the promises of the compiler are really counterintuitive. The translation from one to the other is really straightforward. The compiler should be able to do much more out of it. Okay, so let's try the OpenMP offload. Okay, so now we have to decide on the options that will come at play. Will be converted. MP equal GPU. So we don't use ACC technology, but MP of OpenMP. But we say that this is the GPU part of OpenMP. Okay, so very much in the same way as for OpenACC, the reporting tells us how things are translated. So as it compiles, I share it with you. Yes, thank you, Vincent. You are right. When you want to execute, you need to have this LD library path properly set. So let me.
Doesn't work yet.
Yes, but you are compiling with the TMP. Okay. Okay, so it compiles, and we want to see how long it takes. Sorry, to run this executable. Not very fast. In fact, this is about the same. We have 10 seconds on the one side and on the other. Okay, but I'm beating around the bush because I do really stupid things that we had already solved on the GPU aspect of, on the CPU aspect of things. But you see that OpenMP on OpenACC, OpenMP target on OpenACC will provide you with similar performances. Okay. So, what is the next step? The one that I have been teasing you since this morning. At least we want to use a standard parallelism. So we called it std_par. And in std_par, we see no directives. We see only a nice do concurrent loop. And okay, it's not completely fair because here I also started to cut the number of steps by 2 in order to do one step in one way, one half step in one way, and one half step in the other way, on better exploiting the GPU. But who said the competition would be fair? Okay. So, instead of OpenMP GPU, instead of yes, the GPU information stay the same. And we want it to be fast. But what will change now is using this std-par is GPU. Things look nice. Really, we have a lot of aspects coming here, lots of information. So let me share the command line. Who takes bet on the speed up? Nobody is betting. Okay, let's hope it's a good surprise. Maybe you were right not to take bet. Okay, so it's only that I stupidly left it silent, on top of which there is something which is written. Okay, so 10 seconds, including the write. So with std-par, with the write, we took the same time as OpenACC on OpenMP. We didn't generate any kind of we didn't need to write any directive to tell which region to parallelize. We only put do concurrent on around our work. Okay, so let us look at, we have put the result in this file. It is from right now, so it's a good thing. And if we write it in some human readable way, it's 7.8 gigabytes of information. So it certainly took some amount of time to be written. So let us change the settings because we'll address the values themselves, the results themselves later. We now are looking for sheer performance. So if we run it without the writing, mm, 4 seconds for 32,000 images. So in order to get the images needed for a 40-second movie, 1,000 images, 40-second movie, we only needed 10%. Okay, we'll write them, so 10 seconds, but not bad. We didn't have to suffer too much, only 3 or 4 years. So, yes, there are still some not so satisfactory aspects to this. So, because you see, I have a lot of almost identical copies of my code, and all of them share a lot of information. Something we had done on CPU was, instead of getting, you see this IDEUS duplication of code, here we have a do concurrent in one way and then in the other. Last week, we had used pointers. And with pointers, we would compute the loop and swap the fields. So it was fast and elegant on CPU. How does it translate to GPU? Anybody taking bet? Okay, first good news, it compiles. How does it run? Faites vos jeux, rien ne va plus. Hmm. 30 seconds. What? It was 10 seconds when we were stupid on doing really nasty cut and paste in our code, and then we wanted to be clever and have pointers. And we take, it's not three times more, it's 8 times more because we were not writing. So it should have taken 4 seconds and not 32. What it tells us is not quite clear because evolves is generating implicit copy out, if not already present, copy in. Oh, but maybe we change the pointer on the CPU side, but then on the GPU side, it realizes, oh, it is not the same memory that I am computing on. So I have to copy it back to the GPU memory. The pointer swapping we do in this modern version on the CPU, on the GPU, is not adapted to the GPU. It was a good idea, it was more elegant, but it doesn't work. We cannot lose a factor of 8 in the speed. So, okay. We'll now move to a more elegant way to do things. So, as you have seen, in this code, we have a large part to declare the commonalities, variable, arrays, data structure, name list. Then we have some initial settings, initialization of the fields, swapping of the fields by pointers in case need be, updating at the end of the run, evolving the run. And here we have kept some old code in the old way and deleting the field. So the hot part of the code is only this evolve thing. And each time we have the copy of all the rest. So let's go for some refactoring to modern Fortran. So I call these solutions the split solutions because the program by itself stayed almost the same. Okay, so notice here we have this counter 1 and counter 2 that are filled by the system clock standard Fortran. This is a nice way to time your program, but if C1 and C2 are usual integer, they should report you the time as microsecond. If C1 and C2 are kind equal 8 integers, the standard tells it should report as nanosecond. Of course, NV Fortran does things in a slightly different way. So it's neither microsecond nor nanosecond. We will see it later. Okay, so the program is the same, and the main module looks like the same. The size of the grid, the logical parameter. You see that there are some attempts at blocking that are at play. And then we have the stencils. So I discussed it in the precision talk. With all these stencils should be good to pass as Laplacian. There are, yes?
If the timing is very sensitive. How do you do something like volatile in C?
How do I?
How do you do sensitive timing? So suppose that you have a very tight loop or something, and you want to make sure that that the compiler doesn't optimize the ordering of certain things. So you want to do something like volatile timing. Is it possible?
I have not used the Fortran command system clock at this low level aspect.
Okay.
The best answer should be to read the standard. So I described how the space of Laplacian compatible stencil can be limited to two-dimensional space plus one constraint of normalization, which tells you that the space of Laplacian compatible stencil is parameterizable with one only gamma parameter moving between 0, 1, 2/3, 1/3 or 1/2. So in the literature, the PK and OP stencils have a name. In the Gray-Scott school, yes, we should rename it stencil GS, Gray-Scott, instead of Wade Pretty. We have another combination on here you can see that something has changed. These stencils, reference stencils, are declared as integer without the normalization coefficient, because the normalization coefficient, can be computed from some constraint as the sum of the constraint, the matrix constraint times the stencil. On the normalization coefficient will be used here in this module in order to have all the stencils on the same basis. We'll be able to compare their effect. Okay, so what changes from now is we only have interface to module subroutine. This module is empty, mostly. For all the subroutine we have been speaking of, there are no more here. Because in modern Fortran, you have what is called submodules. And we put some utilities in, the submodule Gray-Scott utilities is a submodule of the module Gray-Scott settings. It contains itself the implementation of the subroutine. Okay, so you see that for the initialization of the settings, we, as we'll be multiplying Laplacians with diffusivities, we introduce the normalization coefficient inside the diffusivity itself. So, some caveat, if you want to reuse this code in your simulation, please be aware that we introduce a spurious 3-factor because it was nicer. So we change the physical diffusivity in order to fit better the time that we have. Okay, so beside this, not much is changing. Please ignore the attempt at blocking I started. To have more generality, we have some conclusion subroutine, which will rely on some implementation info. And in fact, the second submodule is more interesting. You have multiple implementation of the Grace-Code evolution submodule, because this submodule is the one that has the hot part. So I have put the hot part of the module into a submodule, and I will recompile only this part each time. Okay. As you have seen, my building here is very elementary. I don't provide you with a nice makefile or CMake because we want to feel about the various options and play with it. But at some point, in any realistic kind of environment, you will need to have a proper building system. And you are young, so you will learn it. The good point of submodule is when you have a huge module, if a large part of the module has already been compiled, you don't need to recompile it each time. So even with a makefile, you benefit of submodule. Please use submodules. Before getting further into submodule, I start again on the main file of the module. So among the directives and principles, I told you to always have implicit known, even if it's at the compiler level. Always use private. What you have learned in your generation of object-oriented programming applies to Fortran. Modules should have most of their data and many of their methods private. You should always have it after the use line and after the implicit known line, because at some point here, you can declare that this and that part of my module is in fact public. Okay, so this was one first aspect. One second aspect that I strongly advise is when you use a module, specify exactly what type and what method you really want to use in that module. Don't take blindly everything that comes with it. It will be easier later. On the moment, it takes some reflection, and then you will forget one part, and the compiler will complain. But in the long run, it's a better way to limit the dependencies between modules. Okay, so Vincent, come on, let's compile something. Okay, so yes, we'll start with the sequential part. Okay, so how bad is the sequential part? We will not run it on a very large aspect. Okay, on the sequential part is not on the GPU. We compute, which is this with a simple do loops. And we display something every 2000 steps, and we swap the fields because, of course, they will be defined as pointers. And we update in case we need to write. So, we'll play cautious. Okay, in this directory, I was more sensible on there is this floating point precision. So now we have the standard parallelism, the setting module, and we have the submodule for utilities. And we have the submodule for evolution, and here we have a choice, but we start with the sequential one, and we have the main program. And beside this, okay, so there is no do concurrent, so we can ask the compiler to do magic with the standard parallelism equal GPU. He should see nothing to parallelize. And indeed, it doesn't. So we play on only 320 images without writing. Oh, on top of which we have some segmentation fault. Maybe pointers are not so good. But okay, time is sensible. It would be a bit more than 1 minute to compile it on the full image. And when you reach 1 minute, the input-output may be hidden below. Okay, so this split solution with submodule has passed the first step. So this is not a great news, this segmentation fault. Maybe the pointer, we have seen that they don't work so well on GPU. We just have seen it before moving to submodule. And on top of which, they are likely to be the cause of segmentation fault. What does Valgrind say? In use at exit. Illegal opcode in grayscale setting. So it's likely it did not even finish. Wow. Pointers. Really, it looks it's missing something in Fortran. I'm so disappointed with Fortran. Come on, bring me some good news. When was the first use of pointers in Fortran? First use of pointers in Fortran. From start, we have pointers since Fortran 57, even before Fortran 66. What do you mean we had pointers? What did they do in Fortran 90? In Fortran 57, you pass by reference. You pass value, you pass variables not by value to your function, contrarily to C. You always pass your parameters by reference, which is in its own way a kind of pointer. So we will redesign the code in a very old school way. To capitalize on this. So sometimes we use pointers that we don't really need. Okay. So let me show it for you. Okay. So I will quickly show you the modification we'll be addressing after the lunch break. So instead of using this modern Fortran with pointers, we define the compute routine to take parameters, to take arguments, and we'll call compute from U0, V0 to U1, V1, and then on the second turn back from U1, V1 to U0, V0. And from this, we do not need pointers, modern Fortran pointers, because we use all Fortran pointers. So let us be back after the lunch break and see how it works.
As the auditorium is too big. So thank you everyone for following this lecture this morning. So we'll start again at 1:30 with the presentation of the Surfax. And after that, we will resume the lecture on GPU with more black magic. And then we'll finish with a seminar on Julia, but not the one you are thinking of. Have a great lunch.
Bah, écoute, on se retrouve déjà très rapidement. Okay, welcome back. We have now Mohamed Genai, who will introduce the center in Toulouse called CERFAX in France. So Mohamed, it's your turn.
Okay, thanks a lot. Good afternoon, everyone. Welcome. Thank you for having me here at the Grey Scott School. My name is Mohamed Genai. I'm a senior researcher, and I'm here today to give you a quick tour of CERFAX, almost simply the home of simulation at scale. I know it's a little bit provocative, but yeah, it's worth it. So over the next few minutes, I want to show you three things: who we are and why we exist, what tools and machines we actually use to do high fidelity simulations, and finally some concrete examples of the simulation we run. So here's the roadmap. First, short introduction to CERFAX. Second, I will talk to you about one of our solvers and the machine behind every run, going from national supercomputer to European tier 0. And third, the fun part, which is the real CFD. So you'll see some simulation of turbine flames and quite a few other things so that you can have an idea why we need all this supercomputing power. So let's start right away with who we are. And CERFAX stands for the European Center for Research and Advanced Training in Scientific Computing. Together with our shareholders and partners, we develop high fidelity simulations method. And concretely, that means three things. We do massively parallel CFD for combustion, double machinery, and safety applications. Our physics is systematically validated against world-class experiment. And everything we build is co-developed with the industry and deployed on major HPC resources. So it's not shareware, it runs at scale on the real problem. So if I had to summarize CERFAX at one sentence, I would say that we are trying to do science at scale, from fundamental physics all the way to industrial design. Just so you can picture us, we are based in Toulouse. So it's right on the Météo France site. And being at Toulouse is not a coincidence, because it's the heart of the French aeronautic and space ecosystem. And being close to Airbus, Safran, we have Honor as well. And the rest of that cluster shapes a lot of what we do here at the CERFAX. CERFAX is not a university lab. We are a private civil research company. And that shows also in our governance. We have 7 shareholders that you can see here. So it's major French and European industrial and institutional players who both fund us and set the scientific agenda together with us. So that's part of why our research stays grounded in real engineering problems rather than purely academic ones. They are big companies, big shareholders, but they also come to us for help so that we can treat their problems. A quick bit of history, because it tells you something about how we got here. So CERFAX was founded in 1987 in Toulouse. It was just a small scientific group of just 11 people. And in 1996, it became a private civil research company. 21 was reorganized as CERFAX with the 7 shareholders that I mentioned previously. Today, we are a genuine European reference in simulation and HPC with around 150 people actually on site. So in less than 40 years, we went from 11 researchers to a full-scale European simulation center that grows mirrors exactly what happens into computing power. So we can say that we are just like the Moore laws, we grow with each year. CERFAX is organized around the scientific teams, several scientific teams, so it's worth knowing them. We have the algo team who works on numerical algorithm for HPC. There's the co-op team, the team I'm part of, where we try to work on HPC optimization and sustainable programming. There's the global change team, works on climate change and the environment. energy and safety, for combustion, explosions, that kind of things. We also have the advanced aerodynamic and multi-physics. They work on turbomachinery, aeroacoustics, and several other thematics. And of course, we have the CSG team, our internal IT support that help us keeps all our machines and cluster running. They are there if we face any problems. And also we have an admin team handling the management, the HR, and the finance, legal, and all that stuff. Okay, so that was the who we are part. Now let's move to the second part of the talk, which is the solvers and the big machines behind every run. So at Serfax, we kind of do a lot of CFD simulations, mainly to study combustion. So this can be tricky because of the different order of magnitude and length and time, the boundary layers that we are facing, the big meshes, and also because of the chemical component of the fuel we are using. So for example, on the last 20 years, hydrogen was a hot topic. So studying combustion of hydrogen or hydrogen blended fuels usually demand a lot of accuracy. And this is also bring another issue to all the physics that we are treating here at Serfax. And to answer all that, at Serfax, we develop tools. The most used one is AVBP. And AVBP is a code which is tuned to run efficiently on both CPU and GPU and rely on techniques like adaptive match refinement and reduced chemistry models to keep these simulations computationally affordable. So as I said, AVBP is a homemade solver, and it's built from the ground for HPC. So three things define it. First, there's this massive parallelism that scales to hundreds of thousands of cores with near linear efficiency. Second, it's CPU and also a GPU ready. So we have a portable GPU versions that runs on the AMD accelerator as well as NVIDIA GPUs. And the third part, which is the physics that we are treating using AVBP, is always validated. So we handle reacting flow with semi-realistic chemistry combined with the adaptive meshing, and we systematically benchmark all of this against real experiments to guarantee that we are having the real phenomenon that happens. So this slide is basically a snapshot of the HPC landscape we operate in. And I will not read every line to you, but I want you to notice the diversity that we are having at Serfax. So we're talking about machines ranging from smaller in-house cluster like Kraken and Calypso to much bigger machines from the top 500 giants like Lumi, Leonardo, and Marine, so on. So we have different vendors, we have different CPU and GPU combinations, and different interconnect and so on. And the point is that at Serfax, we don't have the luxury or the constraint of one machine. We have to make sure that our code is portable and efficient across this entire zoo of architectures. But let's zoom into three French machines we use the most on a daily basis. We have the Dastra at CNRS, which is the France's leading AMD GPU system. We have also Genzai at Idris. This is the converged HPC and AI machine equipped with the NVIDIA H100 GPUs, which is ideal when we want to combine simulations with machine learning. And also we have Julio Curie at the GCC with the large CPU partitions, and will also soon be complemented by the Alice Focock exascale system. And of course, we will probably run on those machines as well using the code that we have here at Serfax. But beyond France, we also run on European Tier 0 machines through the Euro HPC allocations. So here I listed the three machines that I like the most by order of which machine I like the most. Starting with the Mare Nostrum 5, which is a machine in Barcelona, Leonardo in Italy, and Lumi in Finland. And these are the systems that let us tackle the truly massive simulations, a billion cells, multi-thousand course cases you'll see in a minute. So let's put some numbers on all of this. So to give you a feel of the scales we actually operate at, so single simulations can involve 1 billion cells and even more. Our production runs that we have typically use more than 10,000 cores, and we use more than 20 different supercomputers. And we work with 20 plus industrial and institutional partners around Europe and even around the world. So this is production scale simulations every day on some of the largest machines in the world. Okay, now this converts to the how, and let's get to the what. And this is the part where I show you what all this computing power is actually used for, and also very fancy videos. And I'll start with this one, which is the turbo machinery. So this is one of the example with a project called Spleen. And as you can see in this slide, when we develop models to simulate such phenomenon, physical phenomenon, we always try to compare to the experiment to make sure we are able to reproduce the result. Most of the cases, we are able to do that. We can also do simulations of explosions. So explosion is a very good candidate for simulation because the scale of the experiment is very low. So here, for example, you can see a lab experience where the size of the explosion cannot be that big. But when we are having much more serious stuff like this one over here, it's pretty complicated to conduct using experiment. So it's nice to have tools like AVP to do that. And when we do this kind of simulations, we run a lot. Like, for example, the importance of having different details that you can see in here, which affect all the physical quantities that we measure up. Battery failures is also another good candidate for large-scale simulations because when battery fails, when the complex multi-species gassing, and the reaction between them is very difficult to simulate, needs a huge computing resources. And with the tools such as Arcan that we develop here at Surfax, we managed to keep the size of the simulation reasonable. And because of that, we can do simulations of batteries up to the size of a container. So Surfax also participate in the carbonizations efforts at our partners. This is, for example, a study for flaring problems, and the idea here is to simulate the different wind conditions and calculate the percentage of methane that goes from here and the methane burned compared to one that is not burned, and optimize that later. And with all the science that I presented, we can produce much bigger simulation like this one, which is a simulation of rotating detonation engines, the next generation of engines. And this kind of simulation usually imply the use of all what we have learned from turbomachinery, combustion, and chemistry that I showed you before. And this kind of simulation is very big, and it's one of the candidates for the use of huge supercomputing resources that I showed you before. And we are also able to simulate a huge wind farm. I like this example coming from a grand challenge that we participated in when they brought to life the Star machines. So during this challenge, the idea was to run on the full machine, and we managed to simulate a whole wind farm field that exists. It's in Denmark, and you can reproduce the physical phenomenon you can see over here. Okay, so I wanted to show you all that so that you can understand that behind this scalability curves like this one, we actually trying to do real science. So having an efficient HPC system and a massively parallel code like the one we have is a great way to produce more science. And hopefully with the progress of the hardware and so on, we will be able to continue doing that. So as you saw, our research relies on three pillars. Have the algorithmic and HPC, decoupling and uncertainty, and the AI for simulations. And with that, we can study different thematics, more or less related to CFD. But Surfax is much bigger than that, much bigger than what I've shown you today. We also run a full training program, which you can find at Surfax website under training. We work on other type of physics. We have acoustics, aerodynamic, BMs, climate, wildfire, which is a very interesting subject as well, and many others. We also increasingly active in AI for simulation and quantum computing. We have several persons at Surfax working on these thematics to prepare ourselves to the next scientific trends. So combustion CFD is a big part of what we do, but it's definitely not all of it. So this is what I call pretty impressive, if you agree. And with that, I would say thank you very much for your attention. You can reach us by email, and we'll be happy to answer your questions if you have any. That's it for me. I hope I respected the time.
Thank you, Mohammed. Thank you very much. And we agree with Barak. It's quite impressive. Lots of projects, lots of subjects. So thank you for this presentation. I'm checking if there's any question here. Yes. Just a second.
Yeah, of course. And for the others, if you have any other question later, if you want to reach out, the specific problem, don't hesitate. And all the people at Surfax be happy to help you on this.
Yeah, I have a question. Of course, the mic was not on, but yeah, once you speak about, for example, your AVP software. So you mentioned that you have a really great scalability. Does it mean that you can, for example, develop something on a laptop and then you have guarantee of scalability if you want to check?
I think it depends on the size of the simulation that you'd like to run. AVP runs on the Mac. We have a couple of guys here at Surfax that are fan of doing that. But I think the main use is on very big clusters. So
okay,
that's the idea of having a couple of machines in here with a good size where we can try some stuff on it. Then when we want to go to a much bigger simulation, we go to the Euro HPC machines or the big systems in France.
Okay. In fact, speaking of the HPC machine, so you show us that you have a bit of everything, in fact, in terms of computing, in terms of CPU, of GPUs. How do you choose the new machines that you want to get in Surfax for the next generation? How do you choose this?
That's a big challenge that the CSG team faces every 3-4 years because we try to change one machine, keep the other one, then we do this in a kind of a loop. We talk with a lot of the vendors, try to benchmark with them our main software, which is AVP, but only to see the performance that we can get in a certain budget of electrical consumptions and money, of course. With that, we try to get the best value parts.
Okay. Of course, I'm pretty sure that you check AVP on these new machines before buying them to be sure that your shareholders will be happy with them?
Not only because we also we kind of a reference with the shareholders. So sometimes we bring expertise. So we can tell them that we tried several hardware. This is our experience with them. This can help them also choose their next machines. So
Yeah, okay.
it's not only for just running AVP, but being updated with the latest development in terms of hardware. It's something that we are expected on, at least from the shareholder.
And maybe your last question after I will leave the mic, but since you have several computers running at the same time, as you explained, is it possible for you to use both of them for one simulation, or it's not the goal because the network is not the same or the storage is not the same? I don't know.
It's not something that I think we did. At least I'm not aware of this. I can probably ask. I don't think that we did this before, but I will ask again. If they correct me, I will reach out.
Okay, thank you.
Okay, thank you very much, Mohamed. If anyone has other questions for you, they can use the Discord, of course. Thank you for the presentation. You had some claps here and also like 300 people watching your presentation. So thank you. And for everyone, we'll be back at 2 for the afternoon with Fortran and Julia.
Thank you. Bye-bye.
Thank you. Bye.
Okay, we are back on the Grayscale School, so we finished the lecture of Fortran with GPU, with a lot of magic happening, and then we'll move to Julia, but not the one you are thinking of. So Vincent, it's up to you.
So back to our discoveries in modern Fortran with GPU, modern Fortran with modern compiler. So we were just comparing two ways of flipping or swapping data. The oldest one was in the same time the most elegant and the most efficient. Let us now compile this elegant and efficient system. So we are in the example split solution, which are the more software engineered solutions to the Grayscale problem. We are using the standard parallelism because it is so much easier. And we are exploiting the capabilities of submodule in modern Fortran. So instead of sequential here, we will use the standard parallelism in Fortran 90. Okay, so you see that when the modules are compiled for the first time, they generate, for most of them, no acceleration information because we have put all the hot part in only this submodule Grayscale evolution with standard parallelism on NVIDIA NV Fortran generated the NVIDIA GPU code for only the loop under concern. Okay, so we already know that it is dealing with the copy in and copy out from the data parallelism variable. It is telling us how many CUDA threads, if one day you have to move your code to CUDA, it will already have provided you some basic guidelines. We check once more to be sure we will not be waiting for too long. The result, we do no writing, we'll do 320 steps. On what we have compiled will be this Grayscale TestD power split. Okay, so we still have a segmentation fault. Why? Certainly because of pointers. But the time was too short, so we can afford moving to the problem with the full size. Okay, so at some point we have to deal with this segmentation fault. So let us correct it. Maybe the easiest way will be to simply turn back the Grayscale setting module. So the head part of the module, sorry, excuse me. So as we decided to turn away from the pointer definition. We will be back to the good old nice allocate. Okay, so this was not expected. Thank you. You're right. Okay. So, of course, it is complaining about the definition in swap. So we'll Emacs the Grace Code utility things. So the compilation goes smoothly, and we can try it again for the runtime, which also is, and we still have this compilation error, so I'm completely at a loss. 3 seconds on the 9/10 is a rather good time. Okay, so we have an unpermitted instruction. Okay. So I don't know if NV Fortran will allow for this very G-Fortran flag, which is fbacktrace, that will give us, okay, it is unknown. So we'll debug it in the old way with GDB. Bear with us. Okay, and then we run. So if I ask for the backtrace, we were in line 96 of conclude Grace Code. Okay. So you see that the debugging information gives you what is the module name, the function name, and also you have the file name where the submodule is. Okay. The problem would occur somewhere in this print, which is only timing information. We can try getting rid of it, as the fields are also not allocated. I mean, they are allocated but allocatable and not pointers. We don't need anymore to delete the field by themselves. That's what we want to see. Okay, so we produce simulation. We produce it fast, and we produce it hopefully right. What have we left to do from now? We would like to display some things. And Fortran has not a very good reputation, not only for strings, but also for graphics production. But who knows? There exists a certain tradition of graphics plotting in Fortran. One of the oldest is a pgplot, which is used in astronomy. And we'll use this to display the result of our computation. Okay. So we already have the file HDF5 utils, which is about the HDF file, HDF5 data, but we want to turn them into some image. And so we'll produce an extra module. Okay. That you can find in array image F90. Okay, so it started with a lot of useless parameters, but here we have some palette for color. When the number starts at level 0, if your level are between 0 and 1, as you are displaying the V concentration, it's between 0 and 1. So between 0 and 0.2, you move from black to green. And then from 0.2 to 0.21, you moved from green to red plus green is yellow? No. The combination of red and green. Red minus blue. Okay, so then at from 01 to 04, 021 to 024, 04, you move to red color on until when you reach 0.6, you are in full white. Unfortunately, there is a lot of old technology here which was not very well documented. And we will compile it with Fortran. So here you see in Fortran I use F implicit known, all the warning, the analyzer is included. So we get back the HDF5 util is already here. We want array image which is, and then we'll use the new program HDF5 reopen image. Okay, and we will not start executing it too soon. Okay, so let us look at this program. It will be reading some default HDF file name, which will be the one produced by our simulation program. It relies on some of the HDF5 utils we have provided. The dimension, the number, the size of the image, and the number of image is already set. We open the file. If everything goes well, we open the file and allocate the data to read one slice. And from each slice, if we can read it, we write this to current image. Okay, so we prepare the file name for the image we will be producing. Okay, you see, this is the equivalent of std, string stream in C++. We write something into a string which will be used as a file name to save the data we have extracted here. We have extracted the CAS slice from the HDF file, and we verify what we have extracted with a few values. In the end, we deallocate the slice, and when we have finished reading the HDF5 file, we have a block to execute the equivalent of a C language system command. We prepare a command as something which is compiled from start. So you build your command from other string constant in order to call mencoder and to produce the movie from the images. So you can produce a movie from Fortran. Okay, it compiles. So now we can set the program to write the data. Now we execute it for good. It rolls on we have it in our dev.shm file. So let me move to some temporary file, we move it out of the memory to put it in the TMP. On the file that we have produced to read the image will be here. Okay. So you see in turn that each slice is analyzed and some data is taken out of it to check the size is correct, the offset is correct. The sum is evolving. We see that the sum of the value in the image is in fact expanding. Now mencoder is playing out. And what do we have in our TMP file? A lot of grayscale images, such as this one. Not good. Something didn't go as expected. So if the images are black, from start till the end. No, something definitely got wrong. So the movie should be black, and indeed it is. What did I miss? Okay, so let me be back to the expected results. So yes, dt equals 0.1. Yes, why was it stuck to 1 here? Let me try it again. So, let's move the newly generated image file. Okay, and generate again the images. Yes, I must have a different name list file displayed out on the one with dt of 1 is certainly too big because of the Euler algorithm. And we will be back to this kind of problems. Okay. So I might have yet another problem. I have yet another problem. So before I find a solution, so these were in the past. At some point, I moved it in some other place. Yes. So let me display for you what we should have seen. So as you can see, it has been generated yesterday. Okay, so the colors are not very aesthetic, but you can see that the weight pretty stencil leads to this kind of diffusion, scattering or diffusion, spreading, which is quite comforting. We have been computing sensible things. Okay. So one of the questions we had before, but this year we have solved a part of the problem. Is, does it depend on the stencil? And are we expected to get things that the literature is telling us So sorry, it was expected to start. Ah, yes, I know what I forgot. Okay, so we'll start them synchronously. So it's difficult to see by eye if there is really a strong discrepancy between these two stencils, which is comforting to us because we are simulating chemistry. It should not depend on our assumptions, up to some level. So more proper approach would be certainly to so you see the first image is this rectangular drop of V inside U, U inside V inside U, and it then spreads out and interact. Okay, so Ono Puri is one of the famed one. The other famous one is the Patrakartunen. Okay. And here also, provided that the normalization is the same for both stencils, we find similar results. So hooray for science. Our simulation is simulating something which similarities. So the colors are not nice, but at least we have something. So one of the simplest stencil that we can expect was the diagonal differences. And now that it is properly normalized, we can compare it. Okay, so there is something hazy in the diagonal differences. Something is not quite the same. The spreading rate is absolutely the same, but we don't feel exactly like we are simulating correctly what happens. So it's not completely wrong, but there is something really different. Okay, so why not start with the simplest of all, the central differences. And this one is used in almost every MPI class because central differences don't need you to have interaction with the 8 corners, but only the 4 sides. So central differences. Okay, so it will be quick and there is no need. Okay, there is nothing. Nothing? So if you display only after 2 images, there is nothing more. Do you have any idea why? So this simulation, it's with a stencil that has passed the Laplacian test. We will go into the detail. It is a good Laplacian, yet the simulation is completely different from the other, and we can go as far as say completely wrong. Okay, so such a stencil will be on when on some edge. It will be 0 on some constant area. So if we move, okay, even the first image, you see that the corners are getting attacked. Can I move it by only 1 image at a time? It's really too fast. Okay, so after 10 steps, it is reduced to only this, and after 32 steps, it is reduced to only a small part, and after 64 steps, there is no more of the initial drop. So your central difference stencil will be looking for sharp drop of the concentration, and it will be 0 outside. So it acts as a term source, as a source term in your equation. Before anything nonlinear can happen, you have to put some source in your du over dt. But it is null everywhere, except where you have this difference. And this plays as the game of life. So when you have the good amount of neighbors, you thrill. But when you have not enough neighbors, you die. And this is exactly what happens. Your product is dying because the number of neighbors counted are counted only on the side and not in the corners. This asks for a lot of questions in our simulation because we know a lot of simulation use this central difference. And we would expect similar result, maybe up to some difference, such like the one in diagonal differences, to appear. Okay, so maybe we should look back at the kind of test we have done. So when you move the first images in the weight-pretty diagram, you see that the inner part also gets thinned out, and you have only the corner that are staying. And after some point, the sides, the edge of your figure, they also disappear, but the parts that are in the corner are continuing. And so from your whole droplet of V in your system, only the corner are contributing to the whole development of the system. Okay. So for the test stencil, now we have exact result, contrarily to what I presented in the precision talk. And we'll check that each of the stencil at play respect all these constraints on the Laplacianness of a stencil. So the first constraint is your stencil should not leave zeroth order traces of the function you are stenciling. The second one is there should be no first order constraint, there should be no first derivative of your function in the direction 1. The third constraint is there should be no first order derivative in direction 2. And then this 2x is there should not be a second order cross derivative of your function, second order diagonal derivative. And this one is the only constraint that should not be 0 because it's the normalization constraint on the stencil. So the expected results are 0 for constraint 0, 0 for constraint 1, 1, 0 for constraint 1, 2, and so on, except for constraint 2s, the normalization constraint. And we go up to constraint on the third order. All the other one should be 0. Afterwards, the constraint on the fourth order, they cannot be satisfied with only 3-point stencil. First neighbor stencils. Okay? So you can see this notation is certainly a bit cryptic, but very concise to express array. And you can display the results for each stencil in turn, and we'll discuss it. So to compute for a given stencil what are the value on the constraint for this stencil, we sum each of the constraint times the stencil, and it is summarized as one number. As all of these have been expressed with integer, the result will be exact. In order to show you that it is exact, I have also the similar one with computation being done in float, where we pass a floating point value of the stencil on the floating point value, and we return it as a floating point value. Okay. Okay, so here are each of the constraints for each of the stencils. First evaluated as integer. And we find, as expected, that the 0th order constraint is satisfied, the 2 first order constraints are satisfied, the 3 second order constraints are satisfied being 0, 0, and some non-zero value for the normalization. And this normalization factor can change a lot about the result because it is playing as a multiplicative part of the diffusivities. So it will accelerate or slow down your simulation if you don't pay attention. Okay, on the 4 last column are the 4 third order constraints. And among these 4 third order constraints, you find 2 that are exactly the same as the first order constraint. So, okay. When we ask if the normalization factor, if we reset the normalization factor to 1 instead of 4, 2 times 4, 4 times 4, 6 times 4, and 3 times 4, every constraint are satisfied. So if we compute the discrepancy to the expected value, it is exactly 0 when you evaluate the stencils as integers. But as soon as you start evaluating the constraint as floats, you have rounding error. So all the discrepancy observed here are expressed as a number of machine epsilon. And I expect you to tell me, but there is nothing smaller than a machine epsilon, except that when you have a computation, inside your register, you have 3 more bits. And if you perfectly cancel all the bits, but this 3-1, there will be 3 bits remaining that the computer will display. And this is exactly the case. We have here less than 1/2, which is mostly the first bit at play. Here we have exactly 1/8 of machine epsilon, which is the sticky bit getting set. And here we have a little bit less than 1/10. So, okay, you will tell me, but less than 1/10 is less than 1/8. So how can it happen? But if you are comparing things next to the limit of an order of magnitude, then the relative effect of 1/8 can be lower than 1/8. Okay, so we have tested our computations. Okay, for the last part, we want to express the fact that we had only 9 degrees of freedom. We had 7 constraints plus 1 normalization, which means we cannot constrain all the orders. The 4th order derivative will persist inside your program. You will be computing by Laplacian into the equation that should have only Laplacian. So the way to go to solve this issue are at least two. We can be looking for a smaller step to minimize the space discretization issues and to get these fourth order derivatives that are like the square of the error of the size of the step. So it will move to small value very fast. You can even imagine interpolating. You run your computation, then you run a computation with twice as many points, and then twice as many points, and you check for the discrepancy, and you interpolate when the size of the step goes to 0. It's much more complicated, but it's a safe way. The other way would be to redo the simulation with 5x5 stencils, because we would have 25 degrees of freedom, so we could encompass a much higher order of derivatives, maybe up to the 6th order. And when the order of the derivative grows, the power of the size of the space size of your steps is also getting much more negligible. Okay. So, beside space, we also have some issue with the time simulation. So, as I told you in the previous talks, the first teaching I received in numerical analysis was never use Euler algorithm. So we have some fast way of doing the computation. Let's look at what the Runge-Kutta algorithm will provide us with. So in this modern setting, and with an established stencil such as the weight pretty. Yes. Before going to this, I forgot to tell you about some horror story here. We have seen that we can express the constraint on the Laplacianness as some matrix that we will contract on sum on the stencil of our choice. So in order to have the same treatment for all the stencils, I normalize them with this formula. Okay, this is tested, this works. What I did was very much in the same sense that C++ has introduced const expr. We have the data from start. We should be able to use it at compile time to know the normalization factor from compilation time. So we compute this as a parameter. It will be compiled by, it will be computed by the compiler. In some cases, the compiler goes so far as to evaluate it in quadruple precision if need be, maybe using a GMP for multiple precision. So you get a lot for your compiler. at least with G Fortran. And afterwards, it is replaced as a number, except when your parameters are arrays of parameters. There is no more symbol relating your constant to its name in your code. It's as if it had been defined, but with type. So this is different from C, different from C++, something else. I was really confident in this one. And the first plot I had was completely black, or completely white, as you have seen. The problem was NV Fortran had compiled it, said, okay, I know this syntax, it's good. And it had put 0 in a normalization factor. So 0 in normalization factor, division by 0, infinities, your simulation is out from start. And no warning. So if you use NV Fortran, don't do acrobatics. Stay simple, or check each step of compilation. This is why I have this warning message. The previous instruction was too complicated for NV Fortran, and I had. So here it's in the Grace code, sorry. Even in the Grace code setting, without Runge-Kutta, we have this problem. And this is why I had to define a variable instead of a constant and to evaluate it at the initialization phase. It shouldn't exist. Sorry. Maybe it's something pointing at, and if we had stencil chosen at runtime instead of compile time, wouldn't it be fairer to the other languages? It would avoid premature optimization from the compiler and so on. Okay. So you see a lot of caution about the normalization. But okay, let us be back to Runge-Kutta. So in this, for Runge-Kutta, I had to change things not only for the evolution step, the odd part, but also for this U definition, because I need intermediate fields, intermediate memory array to put the intermediate result of the Runge-Kutta step. So we allocate a lot more memory. Maybe it would certainly change the blocking aspect of things. So we change the setting. Do we change the utility for Runge-Kutta? Yes, we change the utility because if we compare the utility with the Runge-Kutta one, we have to allocate all these new fields. We have to initialize them. Okay, so maybe we'll get some more error, and we have to deallocate them. Okay. Yes? Another option, yes. Yes, Fortran is not like Perl, but you always have many ways to. Okay, and then when we compare the bigger part, okay, so now we'll have to pass a lot of fields. So the ordering is strange, but the idea is as follows. Instead of one step, we compute according to some so-called butcher's tableau that give weight to the nodes and to the so-called Runge-Kutta matrix that is given here. So even if the Runge-Kutta order 4 algorithm is simple, I chose to implement this generic version using butcher's tableau because you will find as an exercise the so-called cache-carp equivalent of the Runge-Kutta, but with order 5 and an order 4 embedded, if you want to play with higher order. So coding the most generic possibility allows you to go even to the 8th order of dormant prints. And here, we compute the 4 steps of the Runge-Kutta, and we don't have to deal with the swapping because one time we go from U0, V0 to U1, V1, and the other time from U1, V1 to U0, V0. So we have seen the testing, we have seen okay, we should compile. So now that we have found the right way to parallelize the problem with a standard parallelism and do concurrent, you see that for each of the nests, the code is generating all the CUDA activity required for us. So there is, sorry. There is a lot more computation involved, so it will take more time. But this stays sensible. Okay, so I had still some delete on the swapping remaining, but when we look at the resulting dev SHM image file, it is from right now. So something is certainly not working in it. Okay, so we have a problem with the graphic library, but you will see the Runge-Kutta movie by side of the standard one. So this one is the white pretty with Euler algorithm. So it's in spite of the numerical delicacies that we have inserted in our computation, the result stays similar before closer examination, and we should be once more confident in our simulation, know that this result can compare to each other. So, are there questions? So, as for the path we could study from now, we have a large choice. Because we want to study the aspect of blocking, of course, on CPU side, as a factor as large as 3 can be won from it. We want to check if it can play on GPU as well. We want to study the cache cap on higher accuracy ordinary differential equation solution. And also one day get the pyramids working on Fortran. Any specific question? So, Pierre, any specific question?
Don't see question now. Should be clear, I think. Or maybe if you want to show us a little check with Insight, for example,
Ah, yes.
until the break.
Okay. Good idea. So let us be back to a more gross categorization. Okay. So we will run it without. So I am back to the standard parallelism Euler ordinary differential equation algorithm on GPU with standard parallelization. Okay, so my working directory will be this one. So maybe I can. So sorry for the size. Tool help. So we'll run this generated this compiled code. So we'll run our compiled code in this working directory on the environment variable. Okay, let's be brave and start it anyway. So we'll profile the run on the GPU of our program to see if we have something to win over the default parameter given by the NVIDIA Fortran compiler. Okay, so it's getting lost. So it is likely that I did not provide the right environment variable. Okay, so it is set to collect GPU context switch traces. Maybe we would like some GPU metrics, but I don't know why. Tools. Let us look on. Okay, so this library should be better, but anyway, we don't ask for it. Now it should be better. Profiling session to finish. Are we stuck? It looks like we are stuck. Okay, so everything looks nice. Okay. I must get something wrong in this new version. So I have not practiced Insight for some time, and I cannot collect the runtime information that would be helpful to show you that the compiled result does not lose time exchanging data. So I will give the...
Yeah, that's happened sometimes. So maybe it could be nice to give you the two information, but normally if you create the project and then you try to profile it, should be okay, but maybe we can start with NSYS in command
Okay.
line, it will be simpler. Yeah. I will do this in the next presentation, but it's not NSYS.
Insight.
Insight is, I prefer to use Insight for visualization and NSYS to profile, because profiling in Insight, there is too much click for me. So prefer to use the command line.
Yes, of course, the alias is also not defined. Okay, so my bad. No. Okay, yet
So
another
it's a-
one. So it was, I corrected the wrong one.
Yes,
Oh,
because
yes.
you have the CUDA 13.1
Yes.
or 0.0. I don't remember to put. They change the path, of course. The trick.
It would be too easy.
Yeah.
Okay, so it's good. And then
Profilers.
profilers.
Right, system, and you should have some way.
Okay.
Yeah,
So
you have the
13.
version and then you have the insight. And then should be okay. Insight
That's a-
system, I presume, yeah. In
Okay, so now I call this
yeah, because N6 UI is insight, N6 is N6. Yeah, yeah, you have to get used to.
okay. So it kept all the information I provided. And the characters are much bigger as well. Sampling period, environment variable, we have the right path to the LD library path on the nice program. So I can go.
Yeah.
Much better. Thanks.
You're welcome. Well, the cameo and this kind of stuff, it's nice.
These reports contain diagnostic errors. Okay, let's start with the bad news. So, collection of CPU IP backtrace sample or context, switch data disabled. Perf event paranoid level is 3, so perf has not been collecting much, which it is collecting nothing. Profiling has started, no NVTX event collected, that's the process, the use NVTX. No CUDA event collected, that's the process use CUDA, I hope so. No OS runtime library event collected, that's the process use OS runtime libraries, I hope so as well. Okay. So, maybe I should restart it. With perf set on. Okay, perf is working. So I should restart. N6 stopped working. Okay. No, N6 is okay. Much better. So we'll address this issue after a short break of 30 minutes.
Okay, so we'll continue a bit with Insight, and then we'll move to some wizardry with not Julia, but pretty clean. Awesome.
Thanks.
It's up to you.
So we'll conclude with some crucial step in all kind of optimization. We need to measure. We should have been measuring all along. We have been optimizing on first principle, which is not so good behavior, but we are learning. And so measurement, optimization measurement system are difficult tools. They are metrology tools in some respect, and they have a lot of options. And you want to display measurement, so you want graphical interface. Graphical interface are notoriously wide. We selected a two-step approach using NVIDIA NSYS command line interface subject with the profile command, and I gave the full command line. It executed, as usual, the run we are accustomed to, and collected data all along. So, doing so, it generated this CUDA STRM file, and we could, in the second turn, run Insight, which is the graphical user interface that you started to see. And now, opening the file that was generated, as in any kind of graphical interface, we have the display of all this important information we have been generating. So the time scale is in milliseconds, and you see a lot of lines. We see that more than 99.9% is spent in one given context here, and 99 in kernels, 110 in kernels. In particular, these kernel settings, so sorry, but the characters are too big, so we don't see all the detail. But we spend all our time in the Grayscott Evolution Compute 30 kernel. Okay, so we'll see its name appearing again and again over very large number of iterations. So we expect it over 32,000 steps. Which is the case. And so we start with the first iteration, where we see two lines. So this first CUDA hardware line, so we have the main program running on the time that is spent on this CUDA hardware, which is the only GPU card of this machine. And when you select this kernel, you see its description in this part over there. It starts at 0.4 seconds and stops after 3.8, almost 4 milliseconds. And when you go to the following one, here we are counting in microseconds. And so for the next, on the next. And as you can see, it looks like it's pretty regular now. We have lots of very small kernels. So if we would add, okay, so it's a tenth of a millisecond, it's 10 to the minus 4 seconds times 3.2 10 to the 4, it is 3 seconds. So orders of magnitude are correct. Yet, the first kernel is a factor 100 slower. On this, you can see it in this aspect here, all these kind of things, and when you settle on them, you see the display is there is CUDA memory operation in progress. So this is for the green, and for the red. Okay, so here we have page fault in red, another one, and in green we have transfer, hardware to device. So the first run is trying to access the initial value. They are in memory, and it takes a lot of time to get all this information from the device memory to from the host memory to the device. Once the data are inside the memory, then everything gets easy, and you have this very fast pace of computation. Okay. Should I be foolish enough to try it with the Runge-Kutta? Let me try. So we compiled it under the same name. And now I will execute the profiling with Runge-Kutta, which is somewhere between 8 and 10 times slower. Okay. So here the scale we are looking at is not zoomed enough. So Control Z for zoom, or Shift Z for zoom, sorry. So now that we have much more memory used and much more data to move, okay, what do we have here? CPU utilization, for threads. Okay, so we spend time in different kernel now, because you see you have 4 steps in the Runge-Kutta. And so they are on different lines, and we don't spend the same amount of time in each of them. And in a very similar way as what we have seen before, the first part take much more time. You see time in the order of milliseconds. And afterwards, we have times in the hundreds of microseconds. So, should we conclude about what we can bring to Fortran using the GPU? We have seen that we can do it in multiple ways, but there is one which is far easier than the other, and this is this NV Fortran STD-PAR. So we should continue along this way. We don't need to go to very big change in our code that will run on CPU and that will get parallelized, vectorized on a CPU. We can keep the same things. We can keep the good practice, modularity, implicit none, private. All of this stay the same. If we want to have some OpenSAC, OpenMP, we'll have to get back what we used to do with do concurrent to standard do loop. It's painful, but it's workable. Maybe some specific part of your code requires this change of mind. We see not to be too confident with the compiler. NV Fortran makes the most out of your source code, but sometimes is a bit forgiving, a bit too forgiving about the standard. So, long live Fortran. And prosper.
Okay, 1, 2, 1, 2. Okay. Okay, so we'll move to the last part of the day. So it's a seminar. At least that's the first time I made a seminar in a graduate school, so why not, at least. So we'll try to talk about Julia, but not the programming language, of course, because I don't practice this programming language. So we'll try to explain to you a little story. So just to not to do exactly the same thing that Nabil used to do in the school, but unfortunately he cannot join us today. So I will try to do my best to entertain you and make you learn some stuff. So let's talk about Julia, but Gaston Julia for a moment. So Gaston Julia is a mathematician mainly from the last century, and he discovered the Julia set in a complex number, the complex plan, and the idea is to have a series. So you have the Z complex number n+1, and you compute it with the previous version, previous value of Z n to the square plus a constant. And the question is this series bounded? So in other words, if I have point into my complex plan, do I orbit with my series without any problem of convergence? Of course, if I diverge, I have a problem. So that's the main question. And a bit more later, we have another one coming into this game. So here we will use A equals -1 because that's my presentation. I do what I want. So Benoît Mandelbrot generalize the Julia set with a much more general idea. So it's not exactly the same idea. Here you change a constant and Julia change the plan with the same constant, but we will stick to Julia to start. So let's say I want to write a program to compute the Julia set, because why not? So I start with some design. As we explained that to you last week, it's important. So I get my program just to orchestrate everything and to schedule everything. I will get some argument to pass some argument for the image size and this kind of stuff. Some I/O, so here we'll do really something really simple, so only PNG. not fancy stuff, not HDF5, not this kind of stuff. And then computing. And the computing will be one kernel because, of course, we want to do things simpler. So remind also the lecture of last week and the lecture of Monday morning with Joel. So once you want to compute some complex number, you will have some problem. Because the complex number is generally a struct, and a struct will kill your performances. You don't have any vectorization, and that's so sad because everyone is using this kind of stuff. So you have an array of structure. So here I get my struct, and I know if I do that, I kill my performances, and what I want is a structure of array with this struct here. So you can use Eve to use some fancy stuff to be sure that everything is okay, but most of the time here I want to deal with matrices, so I will get a matrix for the real number and a matrix for the imaginary numbers. Normally everything should go according to plan. So let's implement that in C++ just to see what's going on. So I will use my favorite trick, vec data. It's a vector of data, really clear. Don't know which data, but whatever, no problem. So I get my vector here just to have one definition at one place in my program. So if I want to use double or whatever, I can. If I want to use other things that SC vector, for example, a first universal vector, I can. And then a Mandelbrot matrix, really simple, X value, Y value, so real and imaginary, if you prefer. And then a little kernel. So the idea is really simple. Here, no problem about optimization, just clarity. One loop over the rows, one loop over the column, and then we iterate. And that's a really common trick for the Julia set. So you start from your complex plan and you iterate. And once you don't get any more normal number, so a number which is not infinite or not none, you stop. Because maybe you diverge at this point and you don't want to diverge. And you count the number of iterations you survive. And then you remember the number of iterations, you put that in a color map, and normally you have a nice image. So typically I get this kind of result in C++, so from -1 to 1 and 0.7 to -0.7 in y-axis. And if I ask my program to get some help, I have fancy help here for all the options I'm supposed to use with a bit of coloring, because it's always nice to have a bit of coloring. So, okay, I get my program, I'm proud of it, it's working. We can do the same in Rust. So, if I do the same in Rust, I will define with the same design. Of course, I will not change my design. The design is working, so I get a Mandelbrot mat here. I get my iteration. There are a bit more information here because of the kernel, but that's roughly the same stuff. And of course, metadata is the same idea as before. It's in the array of float of F32 in Rust. And my kernel is this one. So here there is a trick. You don't get the while, the while loop. I put the while inside the number of iteration here. So I get mat number of iteration, so a vector, just to get the number of iteration here, just to have the loop, and it's working too. So that's a fancy stuff you can do in Rust. And once you struggle to get everything working, you get your unit testing, you get everything, it's working, you get your result, you are proud of the result, you get an option, less coloring, but okay, it's working. So you are proud of your program. And at some point, you want to share it. And here the problems are coming. Okay, so I want to share my program with other colleagues to start. And of course, my program is really simple. One kernel, few interfaces. What could go wrong? Okay, my colleagues that don't want to compile on their laptop because they don't really understand that, they want to do some science, and I understand them, in fact. Of course, they want to focus on what matters for them. So they don't want to call a compiler, they don't want to be bothered with which dependency or which stuff. And of course, if you want to compile, you don't have the right dependency, the right version. That's a nightmare. So, okay, let's do the work for them. So hopefully I use CMake. As Sébastien said, use CMake. That's a standard. It's a standard for a reason. The good point, CMake has CPAC, and CPAC will do all the packaging for you. That's a good point. Okay, you have to define some stuff, the package name, the package version, other fancy stuff. But okay, if you want to define that by hand, that's you get some information that's not so hard. You get the naming, the version, the author, the description, some README, welcome, some URL, this kind of stuff. You have to change, of course, the thing because operating system disagree on everything. So if it's a Debian-like, you need to do some stuff. It's Fedora-like, you need to do some other stuff. Or for Mac, you need to do extra stuff as well, but you can survive. Yes?
Does it create a fat binary, or what does CPAC do? I never cross-compiled through CMake, so.
CPAC come with CMake. If you install CMake, you get CPAC.
But what's the procedure? Does it, does it create a fat binary, or what does it, what's called CPAC actually do?
Don't really get the question.
So you want to essentially cross-compile, right?
Here, not yet. I just want to create a package to give the package to my colleague, just that.
Ah, okay.
No cross-compiling for now. It will come after, but not yet. So you get this kind of stuff inside CMake, and then you call your CMake with your favorite argument, you compile with make, and then you call CPAC, and magically you get your packages. You are happy with that. Okay, that's a bit long. We have a secret weapon here. We use Phoenix CMake, which is a package which does everything for you. And to do the same stuff, you do that. You say, okay, I pick my version, I get the name of my program, I get a little phrase to describe my program, I get the link, and that's it. Because I'm lazy, I don't want to write tons and tons of stuff. So we can do this way. So you need to have Phoenix CMake to compile and to create your packages, but after that, it's okay. Okay, that's done. Now I need to create my package. So my first colleagues are on Ubuntu, so it's nice. It's my operating system. Normally should be okay. Yeah, but some are on Debian, of course, and some are on Fedora, or some are also on Arch. Okay, how to make this work. The problem is, of course, they don't use the same package manager, of course. Sometimes you have APT, sometimes you have Yum, sometimes you have DNS, sometimes you have Pacman, etc., etc. Okay, not a big of a deal. CPAC is there, so normally should be okay. The other problem is they disagree on what is a lib directory. Sometimes it's lib, sometimes it's lib64, because why not? That's so annoying, but the good point is I use Phoenix CMake, and Phoenix CMake handles that for me. So I get lucky for this one. It's okay. So now, normally, if you are on Ubuntu and you install RPM build, you can build a package for Fedora. It's possible. But the problem is, if you do that, you don't get the right dependency version because, of course, once you have a dependency, and we do have one little dependency, libpng, and if you create a package on your Ubuntu, it will link on the version on the Ubuntu system and not on the Fedora system. Of course, they disagree on the version of libpng, and it's not working. Okay, so I cannot compile my package on my Ubuntu for Fedora. Okay, let's try another thing. So I will use containers with Ubuntu 24, 26. Okay, so it's working. quite annoying, but it's working, come on. The same for Debian, maybe Debian 13, maybe Debian Stable Slim to have small images. Okay, so not really simple. Okay, now I need to do the same for Fedora, I need to do the same for Arch. I have too many images. Okay, so I have to put the images into registry, into GitLab with a runner, with a CI, with everything to make it work automatically, because otherwise I will struggle too much on my laptop. I don't have enough space on my laptop, so I have to delegate everything. It's finally working. That's tough to create some package just to help your colleague, come on. Okay, you have to remember one thing. Once you use CPAC, CPAC will produce 4 packages per operating system. One will be deb or RPM, and you will get a tar GZ, a tar Z, and a SH once you install Pixie SH, for example, this kind of stuff. Okay, so here I get 24 packages per release. I have to store everything. It's a bit annoying, but okay, it's okay. At some point, other people will come to you and say, hey, we use ARM. I say, oh no. Okay, so I need to, okay, now I know the trick, so I can put several layers and multi-arch build for the container, as you use all of them for this school. So I can put the Arch 64, the AMD 64 on the same container, and then we'll pick the right one to make sure that everything is working. Okay, I'll double the number of packages, 48 per release. But it's working, it's working. It's annoying, I double the size of all my pipelines, but it's working. And at some point, people are saying to you, hey, we are physicists. So we work on a Mac. And you say, no, come on, let's be serious. No, that's too much. So how to solve that? Because my program is a tiny stuff, and I get an immense amount of work just to make things working, but I'm a developer, come on, I don't want to struggle with this kind of stuff. So, 10 years ago, a bit more, Anaconda come into the play and say, okay, we will create a rootless installer to standardize everything. So there is a generic package interface for all the languages, so you don't have to change the languages to have the Python installer, the C++ installer, the CMake installer, the Python installer, the Julia installer, etc., etc. I want one, please. I don't want one installer per language. Come on, let's be serious. Of course, there is a problem with that. The very day Anaconda released, all the people from Computing Center had a heart attack at the same time, because of course it's a really big security issue once you permit your favorite user to do everything they want on the system. Of course, that's not a good point. Okay, the other problem was at this time Anaconda was a company and they tried to make money, of course, and of course some people, some people on the open source community disagree with that, so they create Conda, the open source installer, rootless installer, the same with generic package format, so the same idea but with open source. And the really big point is they create CondaForge, and on CondaForge you have everything. If you don't get the package on CondaForge, normally you are really unlucky, because even Macau is on CondaForge and we struggle a lot to put in on CondaForge. Normally you should get there. And by putting everything at the same place, the community is growing. And then we start getting some, we start getting to lollipop and peanuts, as Erwin used to say. And of course, once you increase your community, people are starting to do fancy stuff and not really well-defined stuff. And they add and add stuff, and you get really huge environment. Because it's simpler. You get everything at the same place. What could go wrong? The problem is, of course, it kills distributed file system. So if you want to go in a file system and you want to start your job, you will have a big problem of performances. When I say big problem of performances, could be 20 minutes to do an import in Python. If your distributed file system disagree on that, for example, Ceph, if you underestimate the number of a machine to run all the metadata, it's a problem of metadata, not of volume. We'll see that later. And people realize somehow Python is slow. It's slow to fix the environment, slow to solve it, slow to do everything on that, and you can get stuck after 20 minutes, and then Conda will say, I cannot solve your environment, sorry. You wait 20 minutes for nothing. And you get some cryptic error sometimes because, of course, that's the first one, so of course, gets with some error. Okay, but people are learning. So after that, a few developers say, okay, we will create Mamba. We will learn a lot of stuff with this Conda stuff, but now we will use a more serious language command. We want something faster, we want better algorithm, we want full rewriting of the software, and it's faster and lighter than Conda. It was not really difficult, but still. Sometimes you want no environment at all, so there is micromamba for that. So you don't have any default environment, which for Conda it's 10 gigabytes. So come on, it's a big default environment. But sometimes you still get some cryptic error because they didn't fix everything. They are still learning. And after that, the same team say, okay, we learn a lot of stuff with our C++ Mamba. Now it's time to redo it once again, maybe the last time, at least for now, in Rust with Pixie, as Jean-Marc mentioned yesterday. So let's develop a rootless installer with Pixie, with Rust. So it's fast, they are really clear, and you get a package builder for free in it. So not exactly in it, but Rattler build. We'll see that a bit later. So, okay, nice stuff. On top of that, they said, okay, it's nice to have an installer, but of course, having a repository is better. So let's mirror CondaForge. So all the packages possible, they are mirrored on prefix dev, and that's why I will show you that we will have a bit of time, so I will show you that a bit later. So you get everything on prefix dev with the new fancy stuff of Pixie. So once to give you an idea, once you want to upgrade something in Conda, you get a big JSON file of roughly 400 megabytes, which is a bit big for a JSON file. Pixie has another algorithm with small JSON files and a bit of check to see where to go. So you can download kilobytes and not hundreds of megabytes, which is much better to update, of course. It was not scheduled at the beginning because, of course, you start to do something working and people are using them, and after you get a problem of size, but not before. So now we know, so we can change the algorithm at the very beginning. Okay, so what can we do with Pixie? So I have my source files. I get a Pixie config, so to express what I want in my environment, so the dependency, several environments, it's also possible, and the tasks, which are really powerful, and we'll see that later. There is a log file also, which is really important in Pixie. So the log file will give you all the solved version for all your environment. Exact version with the exact digest, the SHA, etc., and all the URLs. So really important. And the philosophy behind it is to say, okay, let's version everything in Git. So if I make a change, I add a dependency or I change a version of a dependency, and somehow at some point I want to go back in time because I want to check something, I can. I have the exact log file of the past. I can rebuild the environment exactly from the past. It's impossible to do that with Conda, really impossible. That's a really good point. Then If I make a change, I change here, I can, another colleague can get the change and start working with the new version, it's okay, or go in the past or whatever. We can do the same on Computing Center for Must, for example. It's working, but we can do more because we have an embedded package builder. So we can say, okay, let's create binary package and put them into Pixie, into prefix dev, and then I can get directly the binary package if I don't want to struggle with the compilation because not really relevant for what we want to do. It's okay, it's possible to do that. So why splitting environment? Because having a big environment which does everything is really simple to do. So I will get my lecture in C++17 and C++20 of last week as an example. So we want a production environment, so with as less as dependency as possible, because I want something really tiny and that can prove that it's working. So only the strict minimal environment. On top of that, I can build a test environment. So I can have the compiler, I can have the build stuff, so say make, ninja, stuff like this. I can add some other tests like Valgrind memcheck, for example, or mal to check if my memory is nicely used, Macaro to check if my favorite compiler does its job well, or coverage stuff, so gcover to get the coverage for the testing for the pipeline. And then maybe I want to get some interactive tools, so GDB or Kakash Grind or Insight, for example. And since it's interactive, it's more a development environment and not the rest. So in terms of size, we get 42,000 files in the development environment, which is really huge. And 1.3 gigabytes. You see here, the problem is not the size. The problem is the number of files. For distributed file system, you kill the distributed file system with that. But you can say, yeah, but it's nice to debug. I have all my tools. It's really nice. Yeah, but the problem is it's really heavy. You get a complex environment with graphics interface. Not supposed to put a graphic interface on the computing center command. And it slows down the distributed file system. And your favorite system administrator will hate you for that. I swear to you. So let's try to do something a bit better. So here, test environment, 18,000 files, much better, but the size is quite the same. Okay. And production environment, 5,000 files, 140 megabytes. Really, really small. And that's nice because it's faster to deploy. Of course, if you have something of 100 megabytes to deploy, it's way much faster than something of gigabytes. You have less complexity, less vulnerabilities, and if your favorite administrator, system administrator, want to check your project before telling you that, okay, you can compute on my computing center, if it's 400 megabytes and you have 3-4 dependencies, way much simpler to check, rather than if you have thousands of dependencies. And at some point, of course, in terms of security, it's important to have that in mind. So how to set up a Pixie project? So create a Pixie init, you call Pixie init, you will get an empty configuration, and then you have a Pixie toml and you can play with it. So here, at the beginning of the configuration that we will explore today, so I get my package channels, so you get Conda Forge, we have custom channels, so Phoenix and Phoenix Dev, just for development stuff, and to get a proper separation between what we do and what the community is doing. So if you do a Pixie Workspace channel add and you put a channel URL, you will add the channel automatically, and Pixie will update automatically your Pixie toml. Then you can define some CPU architectures, some project name. So you have to be consistent with the project name, otherwise you will have a problem, but really nice. The version. So Pixie will be quite annoying with that. If it's not the SemVer version, it will not work. So respect the SemVer version. Then the author of the project, description of the project, the license, and the home page and the documentation page of the project. Okay, everything is in TOML, it's readable, it's clear. Okay, why not? Then I want to compile some stuff, so I need to add a build backend. So here, CMake, for example, you have a Rust build backend, you have a Rattler build backend if you want to do other stuff. You have a Python build backend as well. Then I can add extra CMake argument. For example, if you want to get a special module path, it's not there inside the build backend CMake for now. It will come at some point. So thanks to the developer, but not yet. But it will come. We'll get them on Discord. It will come. Then you can use variables provided by Pixie. So the prefix, for example, this with a double bracket, it has variable defined by Pixie automatically. So you can use them in your configuration. Then you have the dependency in the host dependency. So dependency, you need to create a package, to build the package. So CMake, for example, Phoenix CMake, this kind of stuff, only for the build. After that, you don't need them anymore. And then the run dependency. So what are the dependency I want to have just to run my program? So here, since it's my Mandelbrot program, it's Phoenix option parser to parse the option and the Phoenix PNG to get the PNG image at the end of the test. So then we want to compile at some point. So I have a lot of languages, so C++, Fortran, Rust, and Python, and they all come with their fancy stuff fancy way to do stuff. So sometimes you want to build, so you can use CMake for C++ and Fortran, but if you use Rust, it will be Cargo. If you use Python, you will use Python directly. Okay, not really the same stuff. If you want to test, you will use CTest, for example, with C++. We'll use PFUnit for Fortran. You will use RustTest for Rust and PyTest for Python, for example. Okay, not really the same also. But documentation is the same. You can use Doxygen for C++ and Fortran, and RustyDoc for Rust, and Sphinx or SYCL, for example, for Python. But the good point is, to install, to create my packages, I can use pixie install-a. That's the same for all the languages. Nice. To do the same, to start the test, I can use the tasks. If I use my Retrobricks backend here, I use the task pixie run test. I define the task test, and I run pixie run test, and whatever the language, all the right PyTest, CTest, PFUnit, whatever, it's okay. You do that in your in a standardized way inside your Pixie TOML, and it's okay. The same for the documentation. Pixie run doc. I define what I want to do to create my documentation, and it's okay. And the good point is, it's unified. If you define in your Pixie projects a Pixie run test, a Pixie a text task, a doc task, and use a build backend, everyone get your project and do a pixie install-a or a pixie run doc, a pixie run test, and everything is working. You don't even have to think about the language you are using. That's really powerful. So how to create a package? Because here, at some point, we want to create multi-architecture packages. As you mentioned at the question, it's important to do this kind of stuff. It's already done. We already have the information in the Pixie TOML. You can say, okay, I want Linux 64, Linux Arch 64, and deal with it. I don't want to know about that. Deal with it. That's working. Just don't forget to call Pixie lock, which is really important. Once you call Pixie lock, Pixie will solve all your environments without downloading the packages. So if you don't have much space on your device or stuff like this, use Pixie lock. It's really fast. Don't need to have a big internet connection. Just get the information of the packages, solve everything, and that's it. And upgrade your Pixie lock, and that's it. Okay, but how to deal with microarchitecture? Because, okay, architecture is a thing, but microarchitecture, it's quite annoying, and you want to get performances at some point. So how to do that? So I will quote Sébastien, but the simple stuff you can do is to not deal with that. So you can say, okay, I know I want to have AVX2 and AVX512F because that's what we want to use for the production. So I want to create only these packages for this architecture and nothing else. Okay? So then you create your packages and you get only the microarchitecture you want. Okay, that's not really an answer, but that's a fair idea. You can also say, okay, you can force recompilation, but if you force recompilation, your colleague will say, okay, but I don't want to recompile everything. If I get the right compiler, the right dependency, it's tedious. I don't want to compile. I'm a physicist. Come on, give me a binary, please. Okay. You can let the compiler do the work for you. So in G++, you can say, okay, you can use function multiversioning in G++, so the FMV, and say, okay, -f hotspot, and say the name of the function you want to have several versions of it. And automatically, G++ will create several versions of your function for SCC2, SCC4, SCC3, AVX, etc. Yes?
When you have overloading, because
I never tested with overloading. That's a really good question. Maybe you are not allowed to overload at some point, but you have another fancy stuff if you overload. I'm pretty sure it's working. But this is an automatic way. The lazy option, I like the lazy option. There is another stuff. Maybe it's okay for overloading. The point here is you will get a big library because you will have all the specification for the function you tell the compiler to use with several versions. So it decreases the size of the binary. But it's working. So you have a big binary. You will use probably only one small part of this binary during your production or for your colleague, but it's okay. Everything is working, it's okay. If you want to do more fancy stuff, it's possible. It's attribute. So if you use attributes, so G++ attribute in your file, in your C++, you can tell the compiler, okay, here I decorate my function with the attribute AVX, for example. I want this version, this exact version of my function compiled with AVX. I can duplicate this function and specialize the function for AVX512. I can do the same for all the versions you want, and you can specify, okay, this function is specified for SSC, SSC2, SSC4, just 3 of them, but because I don't want to be bothered with that, I want this one to be really specific for AVX and this one for AVX512F. But you have to do it by hand, and that's really, really tedious. So I'm pretty sure you don't want to do that by hand, but it's possible. If you really need that, it's possible. To do the same thing, you can also say, okay, I can use an extra library, for example, Phoenix HPC proxy, which does practically the same thing, but what we will do is one package with specialized libraries in them. So different libraries, not one big library, but specialized small libraries. And then you link on the fly, at the link time, you discover the architecture, you say, oh, I want to link to this one. Okay, it's okay. Okay, we still have a bigger package, because the package will handle all the architecture possible, but smaller libraries. So maybe after that, you can clear the libraries that you don't want to use. It's not really elegant, but does the work. Okay. Microarchitecture, it's okay. Yeah, but GPUs, come on. That's the GPU weak. How do you deal with GPU with that? One good point is once you use CUDA, you get your file, your CUDA file, and you compile with NVCC, and then you get your program. The good news is the linking is static. So you don't have any dependency on CUDA once you compile. So your package doesn't have any dependency with CUDA.
Launch the program, right? Like you need CUDA to launch the program now?
I will prove that to you during the demonstration, but you will play with everything I just show you now. we have time, let's do it. Yeah, it's static. I will prove you that there is no dependency. We will check that with LDD, and no dependency once you compile statically. But of course, will say to me, yeah, but okay, it's nice now with the new version of CMake. You can say, okay, I can compile. I can say, okay, enable language, do your stuff. It's okay. It's really simple to do. We will see that also if you have some question in the libraries. But if I use C++, and I do some wizardry with NVC++ because SC transforms are really powerful, I get a program, but it's not anymore static linking, it's dynamic linking, and I need to have CUDA RT. I link on CUDA RT in that way. So I need somehow to get my program with a dependency CUDA RT. The good news is it's possible to have that in Pixie. But the static way is way simpler. So always check with LDD. When you compile, you check your binary, you check if you get the dependency with CUDA or not. If you don't, it's okay for you. You can create a package and that's okay. If you have one, figure out how to get this dependency at some point if you really want to deliver that, or try to do some static linking instead. I never tried to force the static linking in NVC++. I'm not sure if it's possible. Don't have time to check, but it could be a nice stuff to check. So the only thing is you must ensure that your CUDA driver version is greater or equal than the build version you had. So for example, here I will show you packages with CUDA 13.1. So working with driver 580. If you get driver 575, for example, pretty sure it will not work because I'm not sure it supports CUDA 13. But if you have a nice updated CUDA, it should be okay. So that's limitation. You can also add this all major option here to say, okay, I want to compile with the all major version of CUDA architecture, which is the new stuff that we have now with CMake. Before it, we had to say, okay, I want this compute capability, this one. It was really long and tedious. Now you say, all majors, deal with it. I don't want to have the details. It's okay. So let's do an implementation in CUDA because we know how to do in CUDA. So I get my Mandelbrot matrix with the pointers, of course. So I allocate the pointers with the CUDA malloc. And then I get my kernel here. So here I have a really small condition just to not have some padding problem. And then my while. And of course, I don't have the for loop because the GPU will do the for loop for me. Really simple. So what can we do once we have a standardized way to do some packages, to do some tests and some documentation with C++, Rust, Fortran, Python? The good point is you can develop CI component in GitLab or GitHub Action if you prefer to use GitHub. And you can manage a unified workflow for all your projects at once. You don't have to redefine your CI inside each project. You can say, okay, I will factorize everything, put that in one project, one GitLab component, for example, and reuse it several times, which is really, really great to do. So we can use packages with a prefix and container registries to get the containers. And so if you have a big monolithic project and you do one change, at some point you will have to you will have to recompile everything because that's why the project is working, and you have to retest everything, and it's not really always relevant because you change a really small part and all the other change, and maybe they are not affected by that. And you get also to, if you want to get one functionality, you get to download the whole project and not only the tiny thing you want to use. And in terms of flexibility, that's not really nice. Because of course, for example, if you use Qt, if I want to parse some XML, of course, I don't want to download Qt just for that. It's a bit too much. So what about here? You get a lot of inertia. And so less releases, because one release costs a lot to produce. We have big packages, and you don't really want to do that. But instead, you can break down your big project into a constellation of projects with this unified workflow. And if you do that, if I have a change here, maybe this project really needs this change because it's a new feature and I want this feature fixed and I want really this fix. I need this fix for this project, so I have to rebuild it also. But not the other. The other will auto-update because you don't use a pin version, you use a range version. That's the default of Pixie also now. And you don't say, okay, I want the version 1 of the project. You say, I want the version 1, but less than 2. And all the other are okay. Of course, you need to follow the same ver convention. If you change your version because it's rainy, will not work. But if you change the version because you have a breaking change, you add a feature because you had a feature in it, or you change a fixed version because you fix something, here everything will work. So here you get smaller pipeline, really smaller pipeline, a shorter compilation time because of course the project is really small. And you have a larger reusability between the project, which is really nice also. And you have a lot of flexibility. And if you get some interchip and you don't have to put them into this big wall, you can say, okay, use this tiny project and play with it. And if you're confident with it, use another tiny project, etc. And it's really smooth to get also some people involved in a team. So in terms of CI components, so we use GitLab. So let's talk a bit of GitLab CI components. So we can do this kind of stuff. So we can say, okay, I use this component, this workflow, which defines everything for me because I'm lazy. I don't want to do this kind of stuff, or at least I do once, not more, not much. Then I say, okay, I want to support these architectures automatically for my package. Then I get the test, the coverage, the documentation, all the relevant stuff I want for my pipeline. I define the package name. I can define some runners. So here we use must as a runner. And we have also a big bonus. It's the ID of the Zenodo publication. So Zenodo is a big catalog of program hosted by the CERN, and the idea is to make sure that once you create a software, the software will not disappear, and you publish your software to Zenodo, you can quote it and cite it as a publication also if you need this kind of information. That's really powerful, and that's automatic because of course we don't want to be bothered with that. So good point. Of course you can reuse it. We developed that for this purpose. So if you are on GitLab and you want to have a look, don't hesitate. Pick the project and have a look and try to use it. If you have another GitLab than the GitLab of the computing center in Lyon, no problem. You can clone it. There is no problem. It's here to be used. So if you want to have a look, don't hesitate. In terms of pipeline, we get this kind of stuff. So it's really, really quick pipeline. So we start to ask ourselves, what is the next version of the program? Then we use Pixie. So we do the unit testing, the coverage, documentation, the packages, everything. And the packages, we have little two here because we have MD64 and Arch64 automatically. Then we push the packages in prefix in our dedicated channel. Then we can do some pages. So we build the documentation and we push the documentation in the pages of GitLab. So we get the same ID for GitHub also. Then we use semantic release. So the idea of semantic release is to say, okay, let's determine automatically if what will be the next version of the program based on the commit. And the idea is you follow convention, and if your commit starts with a fit column, you say, okay, it's a feature. I will increase the feature. So here if I get main version, feature, and fix, I increase the feature if I had a feature. I increase the bug fix if I get a fix. I increment the version if I make a breaking change in capital for For semantic release, it's capital. And then you can have perf improvement, so it will be in feature. Documentation, it will do nothing. Refactor, also you will change some stuff. So you have plenty of convention like this. And that's also, even if you don't use semantic release. Vincent agrees in the Muppet Show banquet at the end of the auditorium. That's really important because the history of your Git is not something to do some statistic on it. It's a tool. If you go back in the past, you should have a precise idea of what's going on here at this time. So is it a fix? Was it a fix, a feature, a breaking change? For what reason? That's what matters in the history. Not test number 32. I want to get some sleep. Come on, it's horrible. That's not a commit, please. Think about your colleagues. Think about people going to your team, your internship at some point. Clear stuff. You can do some joke, but clear stuff is important. So then we push on the Zenodo, and we do the deployment of the documentation at the end. And we get that with 50 lines of configuration. Quite fair for all the projects we are working on. So really, really efficient. So some words about the future, because the future is coming. So previously, the best thing we can do is one package, one big package with a lot of library in it, specialized with different architecture. That's not really nice. What we want, in fact, is to have several packages with several architectures and with the same name, because we want the package manager to deal with that. We don't want to have a big binary and then say, okay, I have to drop 90% of what I download because it's useless for my architecture. The good point is there is currently an update for Conda packages description, and this update, the goal of this update is to update and to ensure the package manager will be able to handle itself the microarchitecture, and the same for the GPU. So we'll get the level, so 1, 2, 3, 4. It's not really precise yet, but there is some development going on. So at some point, your favorite package manager, if you use Pixie, for example, will be able to determine automatically your microarchitecture and pick the right package of the microarchitecture and not the other one. So it's not there yet, but it's coming. And I will finish with a little bonus, and then we'll pass to the hands-on, since we have time. Think about your favorite project. Think about the project you are working on. You struggle a lot, you work a lot, you put a lot of effort in it. What is your reaction if I tell you that tomorrow you should remove one dependency of it, for whatever reason? Because there is a security problem, because it's not the right license, because whatever the reason. What is your reaction? Think about it for a moment. Can you repeat the question, please? Think about your favorite project, the project you are working on here, simulation, data analysis, whatever the project is, your job, your project of your job. And what is your reaction if I say to you, or your boss saying to you, tomorrow, one dependency of your project has to change because you cannot use it anymore for a license reason, for security reason, whatever the reason? What is your reaction? Yes?
The less dependencies, the better.
Yes, but that's too late. But it's a good point. Yeah?
I want a dependency that does the same things with the same API, but without the same problems.
Yeah, but again, that's a bit too late because you have the problem, you face the problem, and you say, I have to fix the problem. But okay, I get 4 answers for you. The first one, which is really common in a big experiment, is to say, so if I get one dependency and I say, okay, we should remove totally this dependency for whatever reason, again, we don't care about the reason, that's a fact. let's say I want to get to from the orange dependency to the green dependency, whatever it means. You can say, okay, people can say it's not possible. It's not even a thing. It's not even possible. So no, never, not even, no. Generally, people will complain a lot with this kind of stuff. No, just no. Do what you want, but no. The answer is no. You can also say, another I found, say, not my problem. You forced me to use this crappy dependency. The dependency is dead. That's your fault. It's not my fault. Okay, that's not really fair, but come on. A number of times people are coming to us with a broken dependency and then they say, oh, fix it. No, I don't have time for this crappy stuff. Okay, what is the very problem of the first answer once you say it cannot happen? The problem is you will have to redispatch resources of your team to maintain the library which is dying. Because you don't want to leave it for obscure reason. Okay, but if you do that, of course, you will split your team into at least two parts. One will continue to work with fancy stuff and they like it and it's okay, and the other will be struggle with this crappy dependency that if it's dying, maybe it's for a reason. And the very problem here is not the fact that you have a dependency missing. The very problem is your software looks like this. And if I say to you, okay, change the orange dependency to a green one, you say, of course it's not possible. This software is sick. Of course the software is sick. And you don't want to change it because it's too much work to do. The second way you can answer this question is to say, okay, okay, it could happen. I'm not really fond of that, but it could happen. So I get my, my program like this, and I will change it like this. Not really fun, but come on, we can do that. Will take some weeks, will take maybe a month, but okay, we can survive. Not really fun, but we can do it. Or you can say, of course it will happen, I pick a dependency, but of course this dependency will not stay for 30 years, of course. Because most of us in the team of the Grayscott, we have to maintain really long-term software, so 30 years. So of course we think about this kind of stuff and say, of course, if I pick a dependency, the dependency will die at some point. We have to change it really quickly. So we can say, hey, if I have a backend, say, okay, let's change the backend, and I have only this kind of stuff to rewrite, just to be compatible with the next one. And the good point is, I have only to do it once. If my my light blue is using the green backend and my blue is using the green backend, I develop this one once and I reuse it twice, and that's it. I don't have to change everything. That's really powerful. So to summarize, in terms of the reason of the problem, if it cannot happen, the technical depth is a bit too much, let's say. So the fact that you have dependency missing shows to everyone that there is a big problem in the software, in fact. If you say it could happen, you can say, oh, okay, it's not really fun, but it's changing a car tire, come on, okay. I don't want to do it, but okay, we can do it. And if you have some backends, because the design is really important, as Sébastien said to you, I have a broken light, change the light, it's okay, done. Because of the design. That's really powerful. And since we have a bit of time, maybe I can make you play with everything. So if you want, we'll start with the C++ program. Come on, give me, okay, this one. We'll put that in the chat. Or maybe there is some question in the chat. Oh. Question from Hi-Fi. CPAC like Dockerfile and Pixie Toml. CPAC is for creating some packages. So it's based on CMake. So you put some variable in CMake. But yeah, it's not really a Docker file on a Pixie toml. Question from Ron. So do concurrent. Donc do concurrent, maybe it's for Vincent. And now also work on Intel GPU with IFX and AMD GPU with AMD Flang. Okay, we can use. Okay, maybe it's for Vincent. So Vincent, we have good news. Question for if I have presentation slide shared, not yet, but if once we finish, I put them on the site. I promise. Also, but I didn't have time yet. But yeah, it's ongoing. Question from someone. So perf docs refactor do not lead to new release. Perf yes, doc no, and refactor I don't remember. I have to check the documentation. But yeah. A question from Laurent. How easy is migration to Pixie from existing dependency file like requirement.txt? PyProject toml. A PyProject toml is straightforward because Pixie understands the Pixie backend, the Rattler build backend of Python that you use in Pixie, understand what is a PyProject toml. So you have nothing to do. The environment YAML, I'm not sure you have, maybe to redefine it properly with Pixie, especially if you want to split it. Of course, if you do a big blob of all the dependency in Pixie, you will not get to what I want to show you. So it's better if you split everything nicely into a development environment, into a production environment and test environment. But yeah, you are practically done if you have a PyProject. If you have requirement.txt, you just have to specify the dependency inside the toml, the Pixie toml, but it will be okay. Is there any automated support to project you try to be recreated manually? We did that manually, but Pixie is really young. Pixie is a 3 years old project, so not sure if we have automated way to do that. But for us, it was not a big of a deal to do that manually for all the projects we had. So. Quite okay. Specialize if you specialize everything and you do everything the same for the project is quite straightforward to do. Question from Luca. It's a bit abstract for me. What's the difference of software implementation between the last two examples if there is broken dependency? In the second case, you rewrite the dependency. And the last case, just the API. Not exactly. Maybe it was not clear. It's a good point. I will just show you here. So here, you have to change a big part of your a part of your program. Not everything, but just a part, because you did your job well. In fact, you change this part to this one. So you have to redevelop this one to this one. And maybe it's not, for example, what I can get as for example, let's pretend you have, here it's an interface, and I use, for example, I want to automatically start jobs with I don't know, Slurm, for example. So I have a file here, and I get my dependency, I create the call that are supposed to be done, and I call them, and it's okay. And suddenly people are telling you, okay, you cannot use Slurm anymore because we moved to another scheduler. Okay, that's life, because whatever reason, and you have to change it. So here you have a file, and you have to rewrite the file to use htconda, for example, or the stuff. Not really complex, but you have to do it once. And you have to rewrite your interface to call everything. So it could be a bit tedious. The point here is once you have this kind of design, maybe I did not elaborate too much on this one, that's why you don't get it. But here, you can say it's a backend. My backend is a type def. If I use another backend, I change the type def, and that's it. So I change one line. So I change the configuration of my PXTML to use the auto dependency, and if I use the same interface, I change one line of my C++ program, I change the type def, and that's it. I already show you this kind of sorcery in the Rust webinar, if you want to have more information. So it's much more powerful. Here you can survive. You can say, okay, I did my job, not the best way, but a decent way, so it's okay. But as Sébastien said to you also last week, you have to constantly keep track of the complexity of your program to make sure that you load the complexity regularly to not explode. Otherwise, you will get the first example here. So that's a day-to-day work, in fact, to have this kind of stuff. But if you have a really good design, the more design you have and the less problem you will have, because you will be able to foresee all the problems that could happen, most of them at least. So that's a good point. Okay, Luca is happy. So a question from Vincent, the purpose of the API is to be reused between project library. Yeah, that's it. That's exactly it. So I don't remember if I, so now, yeah, we have a bit of time, so we can play, you can play with it because that's the goal. We'll start with the first one. So if you have Pixie on your machine, you don't need to have a big computer for that. It just, come on. No, you don't want? Okay. Okay. My keyboard is tired. Okay, my keyboard is really tired. Come on. Maybe it was a bit too much. Discord, come on. I have to learn patience again, I think. Okay, this one. Okay. Bit too much. Please, Discord. No. The other way. Yeah, okay. Okay, my Discord is dying. Please, yes, no, maybe. Okay. Discord is not written for HPC purpose, apparently. Okay. So here, basically, the point is you have the project, the full project I developed for this seminar. So it's a seminar, so I didn't have time to write a full lecture about that. That's why it's a seminar. But normally you should have enough information on it. So I create my Pixie init, so you can do that in every directory you want. You add the channel for the Phoenix channel as I presented to you before. You add the Phoenix Mandelbrot program package, And then you can pixie run the go out of quad blood, then hit enter. Yeah, it works. So thanks for the help, it works. And here, normally, if you do that, or maybe I can do it also to show you. So normally it will not be ultra slow. So if I do that, Vincent, is it okay? I try to put everything at the same size, but that's an improvisation, so it's okay. So here you get directly one package compiled with the CI that we have, so the full workflow I presented to you. So nothing about my computer, just in the CI we had. And then if I do that, we'll solve the environment for me. Oh, okay, there is one package, so it's really fast. And then I'll call my Mandelbrot compute here. And if I pick, okay, here, command, nice. So here in my Mandelbrot CPP, I get my picture here. And you should get the same one, of course, here. So I will let you the command if you want to get that. How is it going? So if you don't have Pixie, you can use prefix dev to get Pixie. You can use Pixie SH. Yeah.
Yeah, I have a question because actually yesterday it was the first time I stumbled upon things like UV and what was it? So I think it was yesterday that it was Python and so
Yeah, UV is really for Python. Pixie is generic, but UV is for Python.
Yeah, is there a link between Pixie and UV and things
They
like
are
that?
both written in Rust.
Yeah, so there's like a new tendency to write tools which are much faster, like this with Rust. Is there a?
It's a global tendency.
Okay.
For example, you get Pixie for the package management. You get UV to replace pip because pip is horrible, in fact. So you get Z, for example, for the development environment. You get SYCL for the documentation. You get Typist to replace LaTeX. A lot of projects are coming to try to replace older one. They are, of course, they are really young, so we cannot judge yet, but it's coming. And in fact, that's normal for a growing community to prove what they can do for the others. So quite fair. Do you get some images? Okay. So now we'll dive a bit into what's going on because, of course, I will not let you and tell you, okay, it's magic, do that. Come on, we'll check some stuff. So here, if you have a look, you get .pixie, a pixie lock and a pixie tumble because everything is done automatically and you get your image. So let's see what's going on in the .pixie. So if I get the pixie, I get env, I get default, because the default is called default, that's really nice. And then I get bin, and I get my Phoenix Mandelbrot program. So that's a binary, and that's a really small binary because the binary is 400 kilobytes. Okay. But if you look at sorts, so if you look at the full size of your little directory here, you will see that it's 32 megabytes. Come on. 400 kilobytes. What's going on? What is going on is we compile everything with Pixie, so with the latest version of libstdc++, and of course I don't have the latest version of libstdc++ on my laptop. So Pixie gets the library, so normally if I get this, I can show it to you. Where are you? 34, 34, 34, yeah. So here, the 6.0.34, on my system, I have the 6.0.32. Too bad. So in the .pixie, I get 21 megabytes of libc++. So if you have an updated environment, or an updated operating system, maybe you won't have this one because that's the magic of a sysroot of CUDA. So that's why we get something big, even if the binary is only 400 kilobytes. So is it okay up to now? Yeah? You want to do some magics with CUDA now? I'm pretty sure you want. So let's do some magic with CUDA. So I will paste only one this time and wait for something, hopefully. We need the music for that. When I passed in Discord and it takes 1 minute for whatever reason. Okay. So here you get exactly the same thing for CUDA. So you do your Pixie in it. You can remove the previous one, of course, not to get too much of trouble. And then the same idea, I add the workspace channel Phoenix. I get my Phoenix Mandelbrot CUDA, as I showed you before, and I run the Mandelbrot CUDA. And if you don't have a too old driver, should work. If you don't, it's not working, but I'm sorry. I have CUDA 13. I put CUDA 13 in my TOML, my Pixie TOML. It's not working. Maybe we can try to do other stuff. But normally it should be okay. At least I checked for several of my colleagues, it was working. So the point is you don't need to have the HPC SDK, you don't need to have CUDA, you don't need to have all this stuff, the CUDA toolkit and so on. You just need to have the driver installed, of course, otherwise it will not work. Failed to connect to GitLab. Or maybe the GitLab is dying. If you are all trying to get some stuff, it's possible that the GitLab will not really survive. So be patient. Could happen. Any AMD version? No, because I don't have a AMD GPU. I would like to do the same for AMD, but I don't have an Adrien to help me for that. So for now, I don't have. But normally, it should be quite the same. We have to check, but we will do that together. We have to check if once you compile with HIP, you have a static linking. If it's the case, normally you can do the same sorcery that I did. You get some images? Yeah. So let's do it here. I will do the same on the fly. Not you. Please, you. Yeah. So we'll do that. Okay, really fast. Of course, the goal is not to compute a lot, just to show you that it's working. And if I go here, normally I get my, come on, thank you. I get my the same picture, of course, because it's the same parameters. So let's see what's going on in this, or maybe I will wait a bit just for everyone to get there. We have time, we have a lot of time. That's okay. So I ask CMake to compile with all the major version of CUDA. So if it's working with CUDA 12, it's okay. I don't have CUDA 12, I didn't check. And none of my colleagues have CUDA 12 yet. So they are all CUDA 13, so I don't know. But normally, even if you have CUDA 12, if you have a smart enough driver, the 580, for example, should be okay. CUDA driver version is insufficient for CUDA runtime version. Sorry, so you have to upgrade your CUDA version. I'm pretty sure, Isabel, you have a CUDA 12 and you should use CUDA 13. I'm sorry for the Surfax. But yeah, normally it should be possible to do several versions, but I don't know how to do that yet in Pixie, but I'm pretty sure it will be not too bad to do this kind of stuff. But yeah, so yeah, all major versions, so pretty sure it will be compatible for all the CUDA 13 something, but not CUDA 12. Maybe if you want, you can get the sources and do the same for CUDA 12 with Pixie Pixie install-A, and we get the package, and then you can get the package to your colleague. Should be nice. Because of course I don't use fancy stuff of CUDA 13. It's just I have this CUDA on my laptop, so I get a nice driver. So what's going on in this environment? So here I can do the same if I have du -h sort -h to see what's going on. So here 33 megabytes, okay, the same stuff as before. So if I do ll of Pixie of default bin Mandelbrot CUDA, I get 1.2 megabyte binary. So we are really far of the 6 gigabyte of the HPC SDK or the 3 gigabyte of the CUDA toolkit. So that's really nice. But of course, 33 megabytes. What's going on? Yeah, I promise you that I will show you that we don't depend on CUDA. So if you get the binary here, you can use LDD to ask the system what are the dependency of my binary, and then you will get really long paths because they are all in Pixie, of course. But here I get Phoenix PNG, I get core options, RT, threads, LD, STDC++, 6, so I explained to you 6.0.34, I get 6.0.32. So it brings back the dependency on my system, even if I already have one, because it's not the right version. GCC S and C, Linux here, PNG here, libm and libz. I don't need CUDA. I don't link to CUDA because it's static. So I can prove you that this binary is static, which is the default once you compile with CUDA. So normally should be nice for you. So as Isabel mentioned, if you don't have the right driver version, you will have some problem. But otherwise, you don't need to have a lot of dependency just for that. To build, yes, you need the compiler, you need CUDA, you need a lot of stuff. But once you compile, it's okay. And oh, yeah, maybe a last point. You will say to me, yeah, but come on, you have no dependency, the computing is cost nothing. Can you prove you that you are using the GPU? Maybe. So if I do some Pixie shell here, and I call, I don't want to write everything, so please. Oh yeah, I can do both. Or maybe here it's simpler, so let's do that this way. You can use Pixie run, or maybe it was not that, yeah. You can use Pixie run and the program here, and you can call the program here. But if you want to use NSys, for example, you can use NSys profile here and use Pixie run NSys something, and it will work. But prefer to use it directly inside my shell. But if you don't want to do a Pixie shell every time, you can do that outside. So if I do that, normally you should be happy a bit, or maybe I need to put the full pass. I don't remember. No, it's okay. Okay, I have a horrible name because I forget to do a -O for the output, but never mind. No, yes, maybe not. Okay, it's nice. So Benny said, if you have any way to do it with AMD, let me know, please. I'm pretty sure with HIP you can do the same, but I don't know anything about HIP, so cannot really help you on this topic. Okay, I will try. Are you happy or not? So I put my insight in really big. Now everyone should see that. So I get my Mandelbrot here. So here, if I make some room. So there is a computing on GPU, but really small, of course, because we compute only one image. If I zoom, or maybe too much, I zoom a bit here. In fact, that's horrible to have a too big interface. That, zoom here. So 8 milliseconds, yeah, it's not too much. So yeah, I get my Mandelbrot compute here, my kernel. And then I'll do some memory. So I did everything in CUDA, so it's explicit transfer. And here I get 100% occupancy for my little kernel. Of course, it's really simple because I don't have neighbors to deal with. I have to focus on one pixel and iterate on it, so really simple. And I install also the, I'm not sure I cannot. Okay, I will do this way, and we'll show you this way, it will be more clear. Come on. Thank you. Here I use the same trick as in the Fortran, as Vincent mentioned you just before. So the block of size 128 to compute, because here I don't have dependency, I don't have neighbor to deal with, so I don't have to be bothered with the exact indexing of all my data. So I can say, okay, it's a full vector, and I split on my full vector, and it's okay. So here 128, it's a strategy of NV Fortran, which is really efficient. You can use 256, which is a strategy of NVC++. But that's why the occasion to check also for this one. So 2 milliseconds here of computing. But I can prove you that we compute on the GPU really quickly, but we compute on the GPU. So it's working. When it's working, it's working. Is it clear up to there? We can move to the last one. Pretty sure we want to do some Rust now. So let's move to the last one, please. Now, okay. So the last one is the same in Rust, because why not? So here, I'm pretty sure that Discord will die again. But I get used to it now, so it's okay. The first time is strange, but the third time it's okay. Okay. So the same exercise. You do your init, you remove what we have before, you do your init. $1.2 MB to use a full GPU is nice normally. Should be proud of that. So here I do my init. I add my workspace Phoenix as before, my channel as before. I install my Rusty Phoenix Mandelbrot package. I run my Phoenix Mandelbrot program. I get my output. So maybe if I do that here, yes, should see everything well. Okay, so here, up, I call my Mandelbrot. Normally, I get everyone here. So here, if I pick my Mandelbrot here, up, I get again the same result, of course, not the same program, not the same implementation, but the same ID. So I get everything coherent. And here, if I have a look, so if I have a look to what's inside, 3 MB. Because of course I don't have the libstdc++ because it's Rust. If I just want to be a bit sassy, I can say, okay, let's check the size of the binary. 1.2 MB. Okay, 3 times more than C++, but come on, that's reasonable. It's okay, and we don't get the libc++ here. And as always, yeah, I can show you that also. I'm not sure if I did that last time. Here you can see that once you compile with Rust, you always depend on GCC-S and libc. But not the libc++, of course. That's why you have a really small environment here, so a 3 MB environment and not 33. Even if the binary is bigger. It's okay up to now? You want to have a look inside the sources, the configuration, the TOML? We have 10 minutes, so if you have some question, no problem. It's okay. Maybe I can show you. Or maybe I can ask you, which configuration do you want to see? The C++, the Rust, CUDA? CUDA? Of course, CUDA. Okay, let's see CUDA. Let's see this one. So CUDA. So here, we'll start with the Pixie TOML. Come on, please. Yes? No? Yes? Okay. Yes. How I'm supposed to do this one? Is it okay? It's okay. So I want to compile with Linux 64 and Linux Arch 64. I do some fancy stuff with the C-root. That's if you get the last version of Pixie 070 and more. They changed, of course, the last time I did the check, it was not working. Now it's working. They changed the way the C-root is handled. So that's a library which does some trick, as if you get the C++, libcd C++, which is the same as your system, they don't pull it again. They get the one of your system because it's 20 megabytes and it's a bit too much. Here, the name of the program, as I said before, the version of the program, the author of the program. I thank my team also for the support for this fancy stuff. Description of the program, the license, homepage, repository, as I said before. I use here the CMake build backend because I use CMake. I have to do some tricks here because, of course, once you compile, you don't want to do fancy stuff inside your CMake files. You want to pass some argument to your program, and a fresh here, not necessarily now. So the module pass to get the dependencies, and the CUDA toolkit include theirs to get the installation with the right include to get the CUDA.h to compile with the prefix that Pixie give me. Then the host dependency, so the dependency I need to build my my package. So I think CMake, option partition, this kind of stuff. NVCC toolkit, CUDA library, CUDA libraries, and sysroot. So a big stuff. I'm pretty sure I can remove CUDA and get only NVCC and some of the stuff, but I didn't have time to optimize this environment. But I'm pretty sure we can gain at least maybe 2 or 3 gigabytes on the size of this environment. Then the run dependency. So as I said to you, I don't link on CUDA stuff, so I don't need to put CUDA inside the run dependency. So only the parsing of the option, the PNG, the zlib for PNG, and the libpng, and that's it. It's okay. And then for the test, well, I can do a Pixie run test, of course, to integrate nicely into the workflow I showed you. I need to get CMake, the compiler, Ninja, sysroot, and the Phoenix CMake, and the CUDA toolkit, and so on, to be sure that I can compile inside the runner. Then some tasks. So here I start, you can have tasks with dependency in Pixie. So here I'll just do my remove build as everyone is doing once you do some CMake, because you put everything on the build directory and then you can read of it and you don't have a mess inside your sources, of course. That's really nice. Then I create the build directory. I call so here you get the full call of CMake. So you have only a part here. So here. Here I add a few options to CMake. And here with the test, since we call CMake explicitly, you can have all the information. So the explicit C++ and C compiler, the explicit CUDA toolkit module pass, the module pass here for CMake, everything. So you get all the information here. Then a task to build a test. So I ask Ninja to build everything. I call the report with ctest. I do the coverage here. So I call gcover to check if the coverage is okay. Of course, the problem is I don't have GPU on my CI because common, so the coverage is not known because I cannot run the test because I don't have GPU in it. I'm pretty sure we can do that with Cocos, but maybe we can do the fancy stuff tomorrow with that, not now. Then the development dependency, if you want some, but I don't do them. I prefer to use my tool on my laptop, honestly, but it's possible. And then documentation dependency, so we have practically nothing. We have mkdoc, we have this kind of docgen and graphviz and stuff like this. And then doc task, so I do pixie run doc here, and I call my CMake with everything which is okay to generate the right Docker file, the right docgen file create the documentation nicely and to push it also to put it in the right directory, and then Pages will do the rest for me. And that's it for CUDA. So yeah, maybe I can show you the CMake also if you want. Yeah, pick the macro. Yeah.
Oh, so I was just wondering, like, do you know about Easy Build?
Easy will where did you get this?
No, like Easy Build is also a package manager to
Yeah,
install.
I never use Easy Will.
Yeah, so
Because
how-
Will reminds me pip, and I don't want to use pip.
Okay, so
That's a
like
PTSD.
in HPC Center, we mostly use Easy Build to install software. You know, the like in condensed matter like Quantum Espresso or VASP or anything like that. So how it is different than this, and then what is the benefit of using Pixie over Easy Build? That was my question.
In fact, I didn't use Easy Will, but can you create some tasks in Easy Will in your configuration? Or it's just a package manager as APT or stuff like this?
So Easy Build, they manage a site to, and once you build something, you can pull and request there, and then it will be there forever, and everybody can use this. This is very easy. So I don't know, but like for Pixie, I'm like seeing for first time, and then you have this huge config file to look after it. Like this is also like auto generated, or you have to manually create this one?
Yeah. The first time it's a bit too much to handle. You get used to it, honestly. The very first time I did not want to use this kind of stuff, and now it's okay for me. It was less than 1 year ago. So honestly, you can get used to it, and it's always the same stuff. You create your doc task, you create your test task, and then whatever is under the hood, because you don't care at the end of what is the language that you are using, it's okay. You just have to do it once, and then we copy paste every time we change. We say, oh, it's a C++ project, let's use the C++ configuration. Oh, it's a Rust project, let's use the Rust configuration, and that's it. So now we have a generator for that also to gain time. But yeah. The first time it's a bit horrible, because you don't really know what to put in which environment for what reason, and it changed a bit, and we asked a lot of the developer to explain us because it was not really clear. But now it's more clear. Yes?
Have you been able to make it work on Windows?
Not know this operating system. I'm supposed to do some computing command, so I don't use it. But with Pixie, you can have the compatibility if you want, but I don't really want to lose a night just to make it compile with an operating system I don't use. So, but it's possible. Pixie is compatible. If you want to use it, you can. If you want a build backend which is compatible, you can. But I don't want to create my sources for that. But you can. Pixie is compatible, CMake is compatible, but I'm not compatible. So that's the problem. Yeah.
Yes, this is a naive question because I've never made. It looks daunting to me to do all these minimum and maximum version.
Yeah,
things.
that's a thing to get, but you need to respect the semantic release philosophy, otherwise it will not work. You can pin sysroot. I pin it because sysroot is a nightmare, but generally it's better. Now Pixie does it by default, so once you do a Pixie add, Pixie will add the dependency inside the toml and give you an interval by default version. Assuming people will follow the SEMVer convention. If it's not the case, of course, you should pass after it and say, oh no, I don't want an interval, I want this version because people are not really serious about that. But yeah, that's really powerful because you don't need to change your
your TOML every time you want to have a fix of this or this project. You can say, okay, I want to be compatible for this version entirely, or for this feature entirely, and not the rest. And so you can get automatic updates, because Pixie will always get the last version which is compatible with the interval you put in your configuration.
Yeah, so a follow-up question. What does that mean that Pixie is aware of features, or is it just aware of dependencies?
Of the version.
Versions?
So you need to respect the sender convention. So if I have if I add a feature, I change the feature number. If I add a fix, I change the fixed number. If I do a breaking change, I upgrade the version. You need to stick to this convention. But if you stick to this convention, it's really, really powerful. And if you have dependency that you cannot really count on, you can always pin them and say, okay, I want this exact version, nothing else, because everything could go crazy. For example, sysroot. Pick a version which is working, you keep it, and it's okay. But for the other, we know that we will be compatible. So, and if you have a problem, you can always get you have the lock inside the Git history, and you say, okay, I go in the past because now it's broken. I get the last lock. What is the version I get in the lock? So you can do a Pixie list to get the version you have in the lock and put the very version inside your TOML to say, no, I don't want to change anymore this one because they bothered me with a broken change. You can always do that if you put the lock in the history. Otherwise, you cannot. That's always a thing to get the habit. At the very beginning, we were not really aware of if we had to give it aware of the sources or not, or inside the history or not. And in fact, in the history is really, really powerful. Question on Discord. Question on Discord. People are saying to me, question on Discord. Okay, we have an easy build. I will have a look to this one. Should be nice. Giorgio said, easy build is designed to build a set of packages for a site. I get the impression that Pixie is more appropriate for creating workflows within a single project. We use it for workflows. That's really powerful. We use it also to create packages and to create the whole environment automatically, because having one package manager instead of 4, it's way simpler to use. I'm pretty sure other people could use Pixie for other stuff, but that's basically what we are doing here. A question from Guillaume: why not just Pixie for dependency? What is the advantages of making it build everything? Just for consistency, in fact, I discussed a lot with Vincent in one of my colleagues in the team. Not the Vincent you know, but another Vincent. He prefers to have everything in the same file. I prefer to have everything exploded into script, but he wins. So in fact, it's nice to have everything. You have one place and you know where is what. You can use Pixie only for dependency. You can create Pixie only with your workspace and say, okay, I want this. But since we use Pixie for also building the documentation, building the coverage, etc., it's really nice. And of course, a thing which is really nice also for me is I hate to start the coverage command on my laptop because the command is horrible. So if I can do a Pixie run coverage, it's really nice for me. So every time, the number of times before I used to just push on the Git just to get my coverage because I don't want to be bothered with this stupid command line. Here I do Pixie run coverage, it's okay. That's really nice. The same for the test, but the test is make test, so command, but yeah, create the coverage, it's quite horrible. And our system is verified by the number of files induce, isn't it a problem on HDD-based cluster? Yeah, if you, on a cluster, I recommend to use really production environment. So not too much files, but not a development environment, of course, otherwise you will kill your file system for sure. So yeah, that's why also Pixie is really nice, because you can really split your environment. You can create as many environments as you want for your needs. And in your laptop, if you want to have everything you can, but it's a laptop, and on the distributed file system, don't do that, because otherwise you will kill the file system and everyone will get mad at you. So you don't want to do that. Okay, so what I said doesn't work for me. Yeah, if you don't have the right driver, it will not work. You need to get, I'm pretty sure, yeah, 580, it's okay. Less, I'm not sure it will work, because it's compatible CUDA 12 and we want a driver compatible CUDA 13.1. So we need to upgrade. Question from Vincent. You don't need to clone, just run the Pixie command. Yeah, you can just run the Pixie command, but if you want to clone to have a look, it's possible. Everything is free open source. You can have a look. That's the purpose of the school, of course. Maybe I can show you. We are late. I swear yesterday we were late. We are late. It's okay. So I can show you a last stuff, except if you have other question, and then we can stop. So here I can show you. So this CMake is really simple. So I use Phoenix to get my my fancy stuff here, some dependency here. But of course, you don't really want to do this one. You are not interested in this one. You want this one, of course. So here, no, the other way, here, a bit more, yeah. So enable language CUDA with recent CMake is really nice. It make everything working for you. CMake CUDA architecture to say, I want all the architecture that you can support. I don't want to do the fancy list as before with the compute capabilities and the optimization capabilities. It was really annoying. Here you say all major, and normally it's working. So here for all the 13 versions should be okay, I'm pretty sure. PNG and CUDA toolkit. Then I print some compiler and stuff to be sure that everything is working. And hide my executable. You don't need anymore to have a CUDA add executable, a CUDA add library with a recent CMake. Everything is inside CMake. You don't need to have extra stuff. That's really nice. Then I do a little for each, because of course CUDA toolkit is not one value but a list from this year. Before it wasn't the case, but okay, that's a nice stuff. And I explicitly get the include the directory and the link directory here with a sysroot for everything to work. And then I link with only, you see here, no CUDA stuff, because everything is done under the hood inside the add executable. So you don't have to worry about that. The CUDA column extra stuff. You don't need to do that anymore. You just have to call that, and it's working. Really smaller than before. That's really nice. Since we are late, except if you have other question, maybe we can. So we talked about set CUDA 13 does not mean lib CUDA RT13 is there. Yeah, but we don't need to have lib CUDA RT13 because we don't link to CUDA. We just need to have the driver. With NVC, in VC++, you need that, but with NVCC, you don't need it. Yes, same error on Kaggle. You want to Kaggle as CUDA 13. Yeah, but 13, maybe not 13.1, or maybe they lied to me and the all measured version is not really okay right now. It's possible. It's possible. Totally possible. Is it okay for you? So thanks for attention. So that's, or maybe I don't know. That's nice for for an end. So thanks for your attention. We will do some Cocos magic tomorrow, and then some cubic root optimization at the end, and we'll show you the plan for the next school also after that. So thanks everybody for joining us today. It was a pleasure also to do some fancy stuff with you at the end of the day. So hope you enjoyed the school. Thanks for all the satellite sites to participating to the school. Thanks for all the sponsors, and see you tomorrow. Bye.